Harvey, MSc PhD. Marlena Dumasari Nasution, PhD. Marcianus Frederick Ezerman, MSc PhD. Presenters and participants, welcome to the second International Conference on Mathematics and Applications, EcoMathApp 2021. Mathematics Department Faculty of Mathematics and Natural Sciences, Universitas Negeri Malang has hosted EcoMathApp annually as researchers, experts, practitioners to share knowledge and insights on algebra, analysis, applied mathematics, combinatorics, computational sciences, geometry, and statistics. I'm Rahmati, your host of this two-day conference. Well, ladies and gentlemen, allow me to read the agenda of today's opening ceremony. The first is singing Indonesian national anthem. The second, welcoming and reporting speech by the chairman of EcoMathApp 2021. The third, welcoming and official opening by the Dean of the Faculty of Mathematics and Natural Sciences. The fourth, opening prayer, and the fifth will be for the session. Well, honorable guests, ladies and gentlemen, now we'd like to invite you all to sing the Indonesian national anthem, Indonesia Raya. Thank you. Next, we will listen to the welcome address and reports from Mr. Muhammad Hafiz, SPD MSI PhD, as the chairperson of the second EcoMathApp 2021. Mr. Hafiz, time is yours.
Thank you, Ms. Rahmati. Good morning, everyone. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Yes. On behalf of the committee, it is my great pleasure to welcome all of the participants to the second International Conference on Mathematics and its Application, or EcoMathApp 2021, which is organized by the Department of Mathematics, Universitas Negeri Malang. My highest appreciation for the 5 keynote speakers, Professor Dr. Toto Nusantara, MSI from Universitas Negeri Malang, and then Associate Professor Walton Pereira Coutinho, MSc PhD from Federal University of Pernambuco, Brazil, and Assistant Professor Marco Morandotti, MSc PhD from Politecnico di Torino, Italy, and Professor Marlina Dumasari Nasution, PhD from Parexel International, Durham, North Carolina, USA, and Professor Martianus Frederick Ezerman, MSc, PhD from Nanyang Technological University, Singapore. My highest gratitude also goes to the invited speakers, Professor Dr. Mariono M. Phil from Universitas Brawijaya, Professor Dr. Surahmat MSI from Universitas Islam Malang, Indonesia, Dr. Rernat Imade Sulandra, MSI from Universitas Negeri Malang, Darmawan Satyananda ST.MT from Universitas Negeri Malang, Indonesia, and Dr. Insinyur Hendro Permadi, MSI from Universitas Negeri Malang. The spreading of COVID-19 in Indonesia has been seriously affected almost all aspects of our activities, including the second peak, which is happened in this year. Regarding this situation and the high motivation to conduct a conference, the Committee of EcoMathApp 2021 decided to keep conducting the conference virtually. The EcoMathApp 2021 chose the theme, the latest trends and opportunities on mathematics research and its application. This is expected to give more contribution from mathematical aspect as a response to the emerging of COVID-19 pandemic. Over 40 abstracts have been submitted, and the presenter will share their research through the presentation regarding the following conference topics, which are algebra, analysis, applied mathematics, combinatorics, computational science, geometry, and statistics. The selected papers will be published in the AIP conference proceeding, which is indexed by Scopus. And finally, I do hope that this conference may give many contribution to disseminating research result in the most relevant area. The EcoMathApp 2021 can be carried out due to the support and full contribution of the several parties. I would like to express my appreciation to the Rector of Universitas Negeri Malang, Professor Dr. Rofiuddin, MPD, the Dean of the Faculty of Mathematics and Natural Science, Universitas Negeri Malang, Professor Dr. Hadi Suwono, and the Vice Dean and the head of the Mathematics Department, Dr. Susiswo, MSI, for all of their support, and also for the organization which support us, that is Indo-MS, Indonesian Mathematical Society. And also I want to thank the committee members for their hard work, commitment, and dedication in organizing this conference. We hope that all participants in EcoMathApp 2021 will gain many insight and knowledge and please enjoy this conference. Thank you.
Thank you so much, Mr. Hafiz. Honorable guests, ladies and gentlemen, the second EcoMath App 2021 is going to be officially opened. We'd like to invite the Dean of Faculty of Mathematics and Natural Sciences, Professor Dr. Hadi Suwono, MSI, to deliver the opening speech, as well as to open the seminar. To Professor Dr. Hadi Suwono, time is yours.
Thank you, Putri, TMC. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum warahmatullahi wabarakatuh.
Honorable keynote speakers, honorable professors, lecturers, distinguished guests, and all participants. Good morning from Universitas Negeri Malang. In the name of Allah Subhanahu wa Ta'ala, and all praise belong to Him for granting us the opportunity to hold the second International Conference on Mathematics and its Application. We call EcoMath App 2021 virtually. It is my pleasure to welcome you all to this conference. The second EcoMath App 2021 is expected to provide a highly competitive forum for reporting the latest development in area of mathematics, such as algebra, analysis, applied mathematics, combinatorics, statistics, and computational sciences. We are aware that the technological advances for a better society could only be accomplished with the support of firm fundamental knowledge. The development of this knowledge could not be separated from the research in mathematics. This conference provides an opportunity for academicians and professionals from various mathematics fields, as well as mathematics and science, to share their knowledge, research findings, and practices with their colleges and the academic community. Therefore, I would like to give my sincere appreciation and gratitude to the notable keynote speaker. First, Professor Dr. Toto Nusantara, MSI from Universitas Negeri Malang. Good morning, Prof. Toto. Second, Associate Professor Walton Pereira Coutinho, MSc PhD from Federal University of Pernambuco, Brazil. Good morning, Prof. Walton. Assistant Professor Marco Morandotti, MSc PhD from Politecnico di Torino, Italy. Good morning, Prof. Marco. Morlina Dumasari Nasution, PhD from Parexel International, Durham, North Carolina, USA, and Martianus Frederick Ezerman, MSc PhD from Nanyang Technological University, Singapore. I would also like to give my appreciation and gratitude to the notable invited speaker. First, Professor Dr. Marjono MPhil from Brawijaya University. Selamat pagi, Prof. Marjono. Assalamualaikum.
Waalaikumsalam, terima kasih.
Profesor Dr. Surahmat, MSI from Universitas Islam Malang. Assalamualaikum, Prof. Surahmat. Dr. Renat I. Made Sulandra, MSI from Universitas Negeri Malang. Selamat pagi, Pak Made.
Selamat pagi, Pak Dekan. Semoga sehat selalu.
Terima kasih. And then Darmawan Setiananda, STMT from Universitas Negeri Malang. Selamat pagi, Pak Darmawan.
Selamat pagi. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. And Dr. Insinyur Hendro Permadi MSI from Universitas Negeri Malang. Assalamualaikum Pak Hendro, selamat pagi.
Waalaikumsalam, selamat pagi Pak Dekan.
Distinguished guests, ladies and gentlemen, a successful conference is the result of many essential parties who have worked hard in planning and organizing ECOMET 2021 during this challenging time. Please let me extend my deepest gratitude and highest appreciation to all committee members. I would like to take the opportunity to say a massive thank to all the participants for attending our conference and bringing your expertise to our gathering. Finally, I hope that this conference will provide useful knowledge, insight, and experiences, as well as improve the quality of research in mathematics. And Bismillahirrahmanirrahim, I hereby officially open the second International Conference on Mathematics and its Application, or ECOMET 2021. Enjoy this conference. Hope you find it intellectually stimulating and academic empowering. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Salam warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you so much to the Dean, Professor Hadisono. Well, ladies and gentlemen, we all expect guidance, wisdom, and support from God as we begin this conference. Would like to invite Mr. Asmianto, SSI, MSI for prayer recitation. Mr. Asmianto, time is yours.
Thank you, Mr. Rahmati. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Let us bow our head for a moment, pray to God Allah Subhanahu wa Ta'ala, so that our international conference can be precious to all of us. I will lead this prayer based on the teaching of Islam, and those who are not Muslim, you are pleased to pray according to each of your belief. A'udzubillahi minasyaitonirrajim. Bismillahirrahmanirrahim. Allahumma sholli ala sayyidina Muhammad wa ala ali sayyidina Muhammad walhamdulillahi rabbil alamin. Allahumma sholli sholatan tunjina biha min jamil ahwali wal afat wa taqdilana biha jami'al hajat wa tutahhiruna biha min jami'i syai'at wa tarfa'una biha indaka ahla darajat wa tuballighuna biha aqsal ghayat min jami'il khairati fil hayati wa ba'dal mamat. Rabbana hab lana min azwajina wa dhurriyyatina qurrata a'yun waj'alna lil muttaqina imama. Rabbi yassir wa la tu'assir bitamin bil khair, Rabbi yassir wa la tu'assir bitamin bil khair, Rabbi yassir wa la tu'assir bitamin bil khair. Oh Allah, today Tuesday, October 26, 2021, in this meeting online, we gather here to bring about an international conference on mathematics and application. The theme is the latest trend and opportunities on mathematics research and its application. Make this international conference a useful science assembly as a medium of sharing useful ideas, knowledge, and experience of scholars, researchers, and students of various disciplines. May the conference we organize today benefit our life, broaden our knowledge, science of ideas, and let us to be successful, productive person, while in turn will boost the dignity of our nation. Oh Allah, guide and bless our hearts and our mind with the light of your guidance. Impart your supreme wisdom upon our activities. Help us to speak our mind clearly. Help us to listen to each other, respect each other, love each other, so that we are input to the blessed person. Oh Allah, protect us from unintended temptation, show us the right paths, and give us knowledge and strength to perform good things. Equally, show us and make it the bad things and give us knowledge and strength to avoid them. Oh Allah, you are the one who can fulfill our doa. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina adzabannar wa adkhilna jannata mal abrar ya aziz ya ghafar ya rabbal alamin. Wa sallallahu ala sayyidina Muhammadin nabiyil ummi wa ala alihi washabbihi baraka wa salam. Subhanaka rabbika rabbil izzati amma yasifun wa salamun alal mursalin walhamdulillahi rabbil alamin.
Amin ya Rabbal Alamin. Thank you so much for Mr. Asmianto. Well, ladies and gentlemen, next we're going to have the photo session. Since we have 167 participants right now, then we're going to have around 8 takes, and the host will help me to capture the pictures. Please turn on your camera and set the conference filter background. Okay, let's start with the first take. I'm going to count to 3. 1, 2, 3. Smile, everyone. The second take. 1, 2, 3. The third. 1, 2, 3. The fourth. 1, 2, 3. 5. 1, 2, 3. 6. 1, 2, 3. The seventh. 1, 2, 3. The last one. 1, 2, 3. Okay, great. We've got all your pictures already. Everybody please fill in the attendance form. The operator will share it in the chat box, right? The operator. Thank you. And we're going to start the parallel session after the break. So we're going to have a break until 9:30. Yeah. So please stay here in the Zoom meeting while you can have a break. Probably you can turn off your camera, and I'm going to meet you again here at 9:30, everyone. See you.
let's rap UM, let's rap more. Hey,
PKKMB Lenceng.
Ciro lupa. Selamat datang kawan di kota pendidikan, Universitas Negeri Malang. Belajar di sini untuk cita impian. Salam cakrawala, itu milik kita.
Percaya diri untuk raih prestasi, tunjukkan jati diri, wujudkan imajinasi. Bergerak selalu, tak pernah diam, giat berkarya untuk capai cita.
Wawasan luas adalah jawaban. That's right. Untuk menggapai masa depan. Pribadi yang bekerja dan saling menghormati pada setiap pribadi tak terkecuali.
Kecerdasan adalah kemampuan untuk adaptasi dalam perubahan.
Universitas Negeri Malang. Berkarya dan terus berkarya. Universitas Negeri Malang. Lambungkan asa menuju cita. Universitas Negeri Malang. Inovasi tiada henti. Universitas Negeri Malang. Lambungkan prestasi untuk negeri. Belajar itu penting, jangan dibawa pusing. Baca buku yang sering, walaupun ongoing. Semangat mencapai impian dengan belajar dan terus belajar. Walau rintangan dan silih berganti, tetap hadapi dengan hati yang sabar. Makan nasi rasanya hambar, hati boleh ambil, tetapi prestasi harus tetap ku
Gunakan
kejar.
pembuktian dan pengalaman, mampu dan adil untuk jalankan kewajiban. Tak kenal lelah, untuk pengalaman yang banyak, jujur dan bijak dalam bertindak.
Beradaptasi dengan Hey yo, let's rap UM, let's rap more. Hey,
PKKMB Lenceng.
Ciro lupa. Selamat datang kawan di kota pendidikan, Universitas Negeri Malang. Belajar di sini untuk cita impian. Salam cakrawala, itu milik kita.
Percaya diri untuk raih prestasi, tunjukkan jati diri, wujudkan imajinasi. Bergerak selalu, tak pernah diam, giat berkarya untuk capai cita.
Wawasan luas adalah jawaban. That's right. Untuk menggapai masa depan. Pribadi yang bekerja dan saling menghormati pada setiap pribadi tak terkecuali.
Kecerdasan adalah kemampuan untuk adaptasi dalam perubahan.
Universitas Negeri Malang. Berkarya dan terus berkarya. Universitas Negeri Malang. Lambungkan asa menuju cita. Universitas Negeri Malang. Inovasi tiada henti. Universitas Negeri Malang. Lambungkan prestasi untuk negeri. Belajar itu penting, jangan dibawa pusing. Baca buku yang sering, walaupun ongoing. Semangat mencapai impian dengan belajar dan terus belajar. Walau rintangan dan silih berganti, tetap hadapi dengan hati yang sabar. Makan nasi rasanya hambar, hati boleh ambil, tetapi prestasi harus tetap ku
Gunakan
kejar.
pembuktian dan pengalaman, mampu dan adil untuk jalankan kewajiban. Tak kenal lelah, pengalaman yang banyak, jujur dan bijak dalam bertindak.
Beradaptasi dengan sekitar, bagai mentari yang sedang berpijar. Jadi diri sendiri, gak perlu basa-basi. Kenali diri tuh, kembangkan imajinasi. Universitas Negeri Malang. Berkarya dan terus berkarya. Universitas Negeri Malang. Lambungkan asa menuju cita. Universitas Negeri Malang. Inovasi tiada henti. Universitas Universitas Negeri Malang. Lambungkan prestasi untuk negeri. Universitas Negeri Malang. Berkarya dan terus berkarya. Universitas Negeri Malang. Lambungkan asa menuju cita. Universitas Negeri Malang. Inovasi tiada henti. Universitas Negeri Malang. Lambungkan prestasi untuk negeri. Hey yo, let's rap UM, let's rap more. Hey,
PKKMB Lenceng.
Ciro lupa. Selamat datang kawan di kota pendidikan, Universitas Negeri Malang. Belajar di sini untuk cita impian. Salam cakrawala, itu milik kita.
Percaya diri untuk raih prestasi, tunjukkan jati diri, wujudkan imajinasi. Bergerak selalu, tak pernah diam, giat berkarya untuk capai cita.
Wawasan luas adalah jawaban. That's right. Untuk menggapai masa depan. Pribadi yang bekerti dan saling menghormati pada setiap pribadi tak terkecuali.
Kecerdasan adalah kemampuan untuk adaptasi dalam perubahan.
Universitas Negeri Malang. Berkarya dan terus berkarya. Universitas Negeri Malang. Lambungkan asa menuju cita. Universitas Negeri Malang. Inovasi tiada henti. Universitas Negeri Malang. Lambungkan prestasi untuk negeri. Belajar itu penting, jangan dibawa pusing. Baca buku yang sering, walaupun ongoing. Semangat mencapai impianmu dengan belajar dan terus belajar. Walau rintangan dan silih berganti, tetap hadapi dengan hati yang sabar. Makan nasi rasanya hambar, hati boleh ambil, tetapi prestasi harus tetap ku
Gunakan
kejar.
pembuktian dan pengalaman, mampu dan adil untuk jalankan kewajiban. Tak kenal lelah, untuk pengalaman yang banyak, jujur dan bijak dalam bertindak.
Beradaptasi dengan sekitar, bagai mentari yang sedang berpijar. Jadi diri sendiri, gak perlu basa-basi. Kenali diri tuh, kembangkan imajinasi. Universitas Negeri Malang. Berkarya dan terus berkarya. Universitas Negeri Malang. Lambungkan asa menuju cita. Universitas Negeri Malang. Inovasi tiada henti. Universitas Negeri Malang. Lambungkan prestasi untuk negeri. Universitas Negeri Malang. Berkarya dan terus berkarya. Universitas Negeri Malang. Lambungkan asa menuju cita. Universitas Negeri Malang. Inovasi tiada henti. Universitas Negeri Malang. Lambungkan prestasi untuk negeri. Hey yo, let's rap UM, let's rap more. Hey,
PKKMB Lenceng.
Ciro Lupa. Selamat datang kawan di kota pendidikan, Universitas Negeri Malang. Belajar di sini untuk cita impian. Salam cakrawala, itu milik kita.
Percaya diri untuk raih prestasi, tunjukkan jati diri, wujudkan imajinasi. Bergerak selalu, tak pernah diam, giat berkarya untuk capai cita.
Wawasan luas adalah jawaban. That's right. Untuk menggapai masa depan. Pribadi yang bekerja dan saling menghormati pada setiap pribadi tak terkecuali.
Kecerdasan adalah kemampuan untuk adaptasi dalam perubahan.
Universitas Negeri Malang. Berkarya dan terus berkarya. Universitas Negeri Malang. Lambungkan asa menuju cita. Universitas Negeri Malang. Inovasi tiada henti. Universitas Negeri Malang. Lambungkan prestasi untuk negeri. Belajar itu penting, jangan dibawa pusing. Baca buku yang sering, walaupun ongoing. Semangat mencapai impian dengan belajar dan terus belajar. Walau rintang dan silih berganti, tetap hadapi dengan hati yang sabar. Makan nasi rasanya hambar, hati boleh ambil, tetapi prestasi harus tetap ku kejar.
Pengertian dan pengalaman, mampu dan adil untuk jalankan kewajiban. Tak kenal lelah, untuk pengalaman yang banyak, jujur dan bijak dalam bertindak.
Beradaptasi dengan sekitar, bagai mentari yang sedang berkijar. Jadi diri sendiri, gak perlu basa-basi. Kenali diri tuh, kembangkan imajinasi. Universitas Negeri Malang. Berkarya dan terus berkarya. Universitas Negeri Malang. Lambungkan asa menuju cita. Universitas Negeri Malang. Inovasi tiada henti. Universitas Negeri Malang. Lambungkan prestasi untuk negeri. Universitas Negeri Malang. Berkarya dan terus berkarya. Universitas Negeri Malang. Lambungkan asa menuju cita. Universitas Negeri Malang. Inovasi tiada henti. Universitas Negeri Malang. Lambungkan prestasi untuk negeri. Hey yo, let's rap UM, let's rap more. Hey,
PKKMB Lenceng.
Ciro Lupa. Selamat datang kawan di kota pendidikan, Universitas Negeri Malang. Belajar di sini untuk cita impian. Salam cakrawala, itu milik kita.
Percaya diri untuk raih prestasi, tunjukkan jati diri, wujudkan imajinasi. Bergerak selalu, tak pernah diam, giat berkarya untuk capai cita.
Wawasan luas adalah jawaban. That's right. Untuk menggapai masa depan. Pribadi yang bekerja dan saling menghormati pada setiap pribadi tak terkecuali.
Kecerdasan adalah kemampuan untuk adaptasi dalam perubahan.
Universitas Negeri Malang. Berkarya dan terus berkarya. Universitas Negeri Malang. Lambungkan asa menuju cita. Universitas Universitas Negeri Malang. Inovasi tiada henti. Universitas Negeri Malang. Lambungkan prestasi untuk negeri. Belajar itu penting, jangan dibawa pusing. Baca buku yang sering, walaupun ongoing. Semangat mencapai impianmu dengan belajar dan terus belajar. Walau rintang dan silih berganti tetap hadapi dengan hati yang sabar. Makan nasi rasanya hambar, hati boleh ambil tetapi prestasi harus tetap ku
Gunakan
kejar.
pengabdian dan pengalaman, mampu dan adil untuk jalankan kewajiban. Tak kenal lelah, ke pengalaman yang banyak, jujur dan bijak dalam bertindak.
Beradaptasi dengan sekitar, bagai mentari yang sedang berpijar. Jadi diri sendiri, gak perlu basa-basi. Kenali diri tuh kembangkan imajinasi. Universitas Negeri Malang. Berkarya dan terus berkarya. Universitas Negeri Malang. Lambungkan asa menuju cita. Universitas Negeri Malang. Inovasi tiada henti. Universitas Negeri Malang. Lambungkan prestasi untuk negeri. Universitas Negeri Malang. Berkarya dan terus berkarya. Universitas Negeri Malang. Lambungkan asa menuju cita. Universitas Negeri Malang. Inovasi tiada henti. Universitas Negeri Malang. Lambungkan prestasi untuk negeri. Hey yo, let's rap let's rap more. Hey,
PKKMB Lenceng.
Ciro Lupa. Selamat datang kawan di kota pendidikan, yeah. Universitas Negeri Malang. Belajar di sini untuk cita impian. Salam cakrawala, itu milik kita.
Percaya diri untuk raih prestasi, tunjukkan jati diri, wujudkan imajinasi. Bergerak selalu, tak pernah diam, giat berkarya untuk capai cita.
Wawasan luas adalah jawaban. That's right. Untuk menggapai masa depan. Pribadi yang bekerti dan saling menghormati pada setiap pribadi tak terkecuali.
Kecerdasan adalah kemampuan untuk adaptasi dalam perubahan.
Universitas Negeri Malang. Berkarya dan terus berkarya. Universitas Negeri Malang. Lambungkan asa menuju cita. Universitas Negeri Malang. Inovasi tiada henti. Universitas Negeri Malang. Lambungkan prestasi untuk negeri. Belajar itu penting, jangan dibawa pusing. Baca buku yang sering, walaupun ongoing. Semangat mencapai impianmu dengan belajar dan terus belajar. Walau rintang dan silih berganti tetap hadapi dengan hati yang sabar. Makan nasi rasanya hambar, hati boleh ambil tetapi prestasi harus tetap ku
Gunakan
kejar.
pengabdian dan pengalaman, mampu dan adil untuk jalankan kewajiban. Tak kenal lelah, ke pengalaman yang banyak, jujur dan bijak dalam bertindak.
Beradaptasi dengan sekitar, bagai mentari yang sedang berpijar. Jadi diri sendiri, gak perlu basa-basi. Kenali diri tuh kembangkan imajinasi. Universitas Negeri Malang. Berkarya dan terus berkarya. Universitas Negeri Malang. Lambungkan asa menuju cita. Universitas Negeri Malang. Inovasi tiada henti. Universitas Negeri Malang. Lambungkan prestasi untuk negeri. Universitas Negeri Malang. Berkarya dan terus berkarya. Universitas Negeri Malang. Lambungkan asa menuju cita. Universitas Negeri Malang. Inovasi tiada henti. Universitas Negeri Malang. Lambungkan prestasi untuk negeri. Hey yo, let's rap let's rap more. Hey,
PKKMB Lenceng.
Selamat datang kawan di kota pendidikan, yeah. Universitas Negeri Malang. Belajar di sini untuk cita impian. Salam cakrawala, itu milik kita.
Percaya diri untuk raih prestasi, tunjukkan jati diri, wujudkan imajinasi. Bergerak selalu, tak pernah diam, giat berkarya untuk capai cita.
wawasan luas adalah jawaban. That's right. Untuk menggapai masa depan. Pribadi yang pekerti dan saling menghormati pada setiap pribadi tak terkecuali.
Kecerdasan adalah kemampuan untuk adaptasi dalam perubahan.
Universitas Negeri Malang, berkarya dan terus berkarya. Universitas Negeri Malang, lambungkan asa menuju cita. Universitas Negeri Malang, inovasi tiada henti. Universitas Negeri Malang, lambungkan prestasi untuk negeri. Belajar itu penting, jangan dibawa pusing. Baca buku yang sering, walaupun ongoing. Semangat mencapai impianmu dengan belajar dan terus belajar. Walau rintangan dan silih berganti, tetap hadapi dengan hati yang sabar. Makan nasi rasanya hambar, hati boleh ambiar, tetapi prestasi harus tetap ku
Gunakan
kejar.
pembuktian dan pengalaman, mampu dan adil untuk jalankan kewajiban. Tak kenal lelah, untuk pengalaman yang banyak, jujur dan bijak dalam bertindak.
Beradaptasi dengan sekitar, bagai mentari yang sedang berpijar. Jadi diri sendiri, gak perlu basa-basi. Kenali diri tuh kembangkan imajinasi. Universitas Negeri Malang, berkarya dan terus berkarya. Universitas Negeri Malang, lambungkan asa menuju cita. Universitas Negeri Malang, inovasi tiada henti. Universitas Negeri Malang, lambungkan prestasi untuk negeri. Universitas Negeri Malang, berkarya dan terus berkarya. Universitas Negeri Malang, lambungkan asa menuju cita. Universitas Negeri Malang, inovasi tiada henti. Universitas Negeri Malang, lambungkan prestasi untuk negeri. Hey yo, let's rap UM, let's rap more. Hey,
PKKMB Lenceng.
Ciro lupa. Selamat datang kawan di kota pendidikan, yeah. Universitas Negeri Malang, belajar di sini untuk cita impian. Salam cakrawala, itu milik kita.
Percaya diri untuk raih prestasi, tunjukkan jati diri, wujudkan imajinasi. Bergerak selalu, tak pernah diam, giat berkarya untuk capai cita.
Wawasan luas adalah jawaban. That's right. Untuk menggapai masa depan. Pribadi yang pekerti dan saling menghormati pada setiap pribadi tak terkecuali.
Kecerdasan adalah kemampuan untuk adaptasi dalam perubahan.
Universitas Negeri Malang, berkarya dan terus berkarya. Universitas Negeri Malang, lambungkan asa menuju cita. Universitas Negeri Malang, inovasi tiada henti. Universitas Negeri Malang, lambungkan prestasi untuk negeri. Belajar itu penting, jangan dibawa pusing. Baca buku yang sering, walaupun
Okay, good morning, Mr. Martianus Frederick Ezerman. How are you today?
Morning, selamat pagi.
Ya, selamat pagi.
How's everyone?
We will wait for the Master of Ceremony.
Pak Fred.
Hello.
Nice to meet you, Pak Fred. Good morning.
Good morning.
Last time I met you in UGM in 2019.
Oh, okay.
Yes, Sims School in coding and cryptography.
Right.
Yes.
That's a 2 weeks intensive course.
Yes.
Yes.
Okay.
Let me put this one on so I hear you more
Okay.
clearly. Okay, good.
Okay, so for the presentation, you want to present by yourself or?
Yes, because I
Okay.
will need to run my my computer code as well, my C code.
Okay, yes.
Belum.
Let me just test it and see if I can do it.
Yes, of course.
Right. So now, can you see this? My
Yes.
PDF?
Yes.
What about the C code?
Yes, yeah, yes, we also see
now
the
you can
C
see the
code, okay.
C code. All right,
Yes.
let's
Okay.
see. Okay, so it runs nicely. It's running, okay. Good.
Okay.
So let me just stop. Excellent. I often pass by Malang. Well, before COVID, I usually go to East Java twice a year.
Oh,
Because
to Madiun?
no, not to Madiun anymore. I no longer have any family there in Madiun.
Okay.
My wife come from Blitar, so we usually go to
Ah.
Surabaya and travel to Blitar.
Blitar,
So we
yes.
pass by Malang, but
Malang, yes.
but we don't usually stop.
Yeah. Okay.
Okay. Hello, everyone. Welcome back.
Hello.
And now we're going to start the plenary sessions. Today, we're going to have 3 plenary sessions with 3 different speakers from 3 different countries. The first, we're going to have Mr. Martinus F. Ezerman, PhD from Nanyang Technological University, Singapore. And then the second, Professor Dr. Toto Nusantara from Universitas Negeri Malang, Indonesia. The third, we're going to have Assistant Professor Marco Morandotti, PhD from Politecnico di Torino, Italy. Okay, to start the marathon of this 2-day seminar, we would like to invite our first moderator, Mr. Muhammad Agung, SPD MSc. As the moderator of our first keynote speaker, Martinus F. Ezerman, PhD. Well, Pak Agung, over to you.
Okay, thank you, Ms. Rahmati. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. First of all, I would like to welcome you to the second International Conference on Mathematics and its Application, or ICOMath-App 2021 plenary session. Today we will have three plenary sessions, and this is the first one. And first of all, I would like to introduce myself. My name is Muhammad Agung from Mathematics Department of Universitas Negeri Malang, and in this session, I will be serving as your moderator. And in this session, you will hearing a presentation from Dr. Martinus Frederick Ezerman. And before we get started, please let me to read a brief curriculum vitae of our distinguished speaker today. So, sure. Okay, so Dr. Martinus Frederick Ezerman is currently a senior research fellow in Nanyang Technological University, Singapore, and he has received his bachelor degree in the Ateneo de Manila University, Philippines. First is BA in philosophy, and the second in BSc in mathematics with magna cum laude. And then he received his master degree in MSc in mathematics, also in Ateneo de Manila University, Philippines. And finally, he received his PhD in mathematical science in Nanyang Technological University, Singapore. And Dr. Martinus Frederick Ezerman is, this is his research fields. First is in coding theory, especially in holographic data representation, error control codes, and then quantum secure cryptography, spectral analysis, and DNA storage and coding. And also in informatic theory, this is the interplace between classical and quantum information, both discrete and combinatorial. And also from the field of sequence, this is our topics in this session about the De Bruijn sequence, especially in constructions and application of De Bruijn sequence. Yes. And also here is some of his publication. First, the news in September 2021 is about 2 new zero-dimensional qubit codes from bordered meta circulant construction. And then we also have about the comparison of distance bounds for quasi-twisted codes and the non-convex and non-concave GANs using synchron divergence, and also an efficiently generated family of binary De Bruijn sequence. So without further ado, now allow me to welcome the speaker, Dr. Martianus Frederick Ezerman, who will deliver a presentation with topic binary De Bruijn sequence for about 45 minutes. And during the presentation, if anyone has questions or comments to Dr. Martianus, please write them down in the chat room of the Zoom meeting. And to all participants, may I kindly remind you to mute your microphone, please, and give full attention for the presentation from Dr. Martianus Frederick Ezerman. So please, Dr. Martianus Frederick Ezerman, the time is yours. Okay.
Thank you very much, Pak Agung. It's nice to see you again, although in the online setup. Good morning, good morning, ladies and gentlemen, students, faculty, professors, researchers. I'm really privileged to be invited to share with you some of my results in De Bruijn sequences this morning. It's a topic that I've been working on for about 7 years now, actually. Started out in around end of 2014, and it's still something that I'm actively working on together with my close collaborator, Zhang Chuling. I'm currently editing a volume for World Scientific. It will be a collection of 10 tutorial and survey papers on sequences. We hope to finish this by the end of the year, and yeah, hopefully it gets published sometimes next year. My work in NTU is 90% research and about 10% administrative matters. It's something that I really like. Unfortunately, in Indonesia, we don't have that kind of setup. So for now, I'm stuck in Singapore. Yeah, so let me begin with what we want to do today. So if you want the slides, I can share with you in chat, or maybe the moderator can share with you also in chat. I've given them a copy of it. The reason is that from time to time, I will refer to a few links in the slides. So it will be handy if you actually have them and you can just click them. We'll focus on today. We'll focus on this specific construction, which is very fast. But before that, I want to guide you through some of the major ideas in De Bruijn sequences, why they are interesting, what kind of mathematics are being used, what kind of questions are still to be investigated. Okay. I also will refer you to my personal webpage. There is my personal webpage there. All the papers that I mentioned here, if not the published version, at least the accepted version, which is very, very close to the published version, they are available there. In the links, you can also find all the softwares. We make the software implementation available openly. for benefit of other scholars and students who may want to, try them on and maybe improve. Okay, so later we will also look at the implementation. I'll show you what they are and how to run them and how you can benefit from them. Okay, so here is the published paper. It's under paywall, so unfortunately I cannot just share it with you, but if you drop me an email, I'll be happy to share with you. In my webpage, I put also the accepted version, which is exactly as the published version, except for the editing, the numbering and everything is the same. I will also briefly mention this paper later, okay? This is published in AAECC, so Applicable Algebra in Engineering, Communication and Computing. There is this other paper which is more suited for computer scientists. If you know how to use Zec logarithm, then you can, here we provide a very comprehensive treatment on how you can generate them. Okay, more on the practical side rather than the theoretical side. This paper is now the state of the art. If you look at the algebraic side of it, because in this paper we discuss completely a huge class of De Bruijn sequences. It comes with implementations. It comes with complete analysis, comparison with the previous works. It took us a year and a half to complete this paper, actually, and another year and a half for the refereeing process, because it's not an easy paper to read as well. But if you're more of a mathematician and you're interested to know the algebra behind it in a more complete way, I will recommend this paper. As I said, this is not an easy paper, that this is now state of the art. The best we have on the covering of LFSR. This is not because I'm one of the authors, okay? It's because right now this is really the state of the art. Hopefully you can improve, you can get involved in improving it. So all of this, if you want to get them, you can just drop me an email. I'll be happy to share them with you. Or you can go to my webpage. Here, the link is here. Under publication, you will have all of the resources you need, including the source code. Okay, so today I will try to be gentle as much as this can be done in a mathematics conference or seminar. But let me start with my main interest at the moment. I promised the moderator and the organizer that I will try to be as gentle as possible. So I hope I can do that today. My purpose is to get as many students and younger researchers to get involved. So I don't want to scare you. Okay, a lot of fun things as well here in sequences, in De Bruijn sequences. So first, just a brief overview of my research work, and so the grant that pay for my salary and my research is from the university. It's a long-term grant, actually. It's a 7-year grant, so I don't have to worry about writing grants very often. So typically I work on these 3 topics: algebraic coding theory. So this is with application in quantum error control, also in cryptography, and more recently for distributed storage. So if you have very large data center or database, you want to be able to distribute them, but you also want to distribute them in an economical way to reduce costs. But also you want them to be robust. So if one of the hard drive, for example, or one of the server went down, you can reconstruct the content from the other portions of the data. I also work in holographic data representation. This is something also very, very fun. I really like to do this. In addition to my research grant, this is also paid for by the Singapore National Research Foundation. And cryptographic sequences, this is the long-term collaboratory project with my colleagues in China. So when I come and visit them in China, the Chinese National Research Foundation pay for my cost. So I want to acknowledge these grant agencies for supporting my research. And of course, my close collaborator at NTU, I work with Professor Ling San. He was my PhD supervisor actually, and now we are colleagues. We're working on research together. We have Dr. Gao Jun, who is a research fellow, a specialist in coding theory, and then Buket, who is one of the world expert in quasi-cyclic code, and Adamas Faresa. Adamas is from Indonesia as well. He is our main coder. So most of the software that we produce in the team is done by him. Of course, we work also with a lot of other people. There is Marcus in Poland, Freddy Brookstein in Technion, and Chang Chuling, my long-term collaborator in the print sequence. He's partly in Chengzhou, partly in Beijing. And Janusz is with the military communication department in Poland, and Stephen Wang in Charlton in Canada. So on the site, not very officially under any grant, I have a lot of other projects, code-based crypto, confidential computing with a good friend in Wollongong. And recently, I do a lot of work in side channel analysis for post-quantum cryptography with Prasanna and Shivam. In Indonesia, I have extensive collaboration with friends in UGM and in Poltek Sandi. We look into lattice-based crypto, and with Pak Mustafa, who is a lecturer at UNY, who he's right now doing his PhD with us. With me and Professor Indah Emilia and Tia Yunia in UKM. I work a lot with dear friends in Samsung Research Indonesia in Jakarta, especially with Risman. He's the head of, now I think he's the CTO of Samsung Research. And also with colleagues in America, with Pani, this metacirculant graph. So these are the things that I'm working on. So if you have interest in any of them, you want to get in touch, you're most welcome. So let's go into the proper material then. So before we start, giving a seminar directly in person is already not an easy thing. Giving it online is exponentially harder, because we get distracted, a lot of other things that occupy our attention. So before we move along, if your situation allows you, please get some blank papers and pencil or pens. We're going to do some exercises together. Okay. I would like to invite you to think together with me. We want to reproduce the examples for yourself. And if you know how to run a C code, you can download the source code from this link. Okay, download it. It's already compiled. So you just, well, no, I'm sorry. It's not compiled yet. This is still really the source code in C++. Please compile it, and then you can run it together with me later. Okay. So, of course, we start with the definition, right? What is a De Bruijn sequence? De Bruijn sequence can come from any alphabet size, any finite alphabet size. So you don't have to deal with binary, but for today, we will deal mostly with binary. That means the elements in the sequence, the strings are formed by 0 and 1s. Okay, the strings are formed by 0 and 1s. And there is a simple condition there. So first, we have one parameter here, which is the order of the sequence. It's a positive integer, but usually at least 3. Why at least 3? Because for 1 and 2, it's not very interesting. Okay, they are trivial. For n equal to 1, n equal to 2, these are trivial. So what happened? You form a string, a sequence, and this sequence is periodic. So after some period, it will repeat the pattern exactly the same. Okay, so this binary sequence, the De Bruijn binary sequence, it has a period 2 to the n. So n is fixed, n is given or chosen, and then you form a string. Okay, the period is 2 to the n. That means every 2 to the n, you repeat the pattern, exactly the same pattern. But what is special about the De Bruijn sequence? Each n tuple occurs exactly once. Exactly once. You see? So 2 things to remember. Each of them, so nothing left behind, everything appears, but they appears exactly once. Okay? So again, I asked you first to get blank papers and pencil and pens, right? So here it goes. Then we need to do it together. We say that 2 De Bruijn sequences are equivalent if they're just cyclic shift of one another. Okay? The equivalent if one is a shift of the other. As I told you, as I have told you, the sequence has a period. So every 2 to the n length, it will repeat itself. Okay? So if you are shifting it you're just shifting it cyclically, then you don't consider it to be a different sequence. It's the same sequence. Okay? So now get your pencil or pens and the piece of paper, and then now look at this sequence. Okay? So the order is 3. That means the period is 2 cubed, which is 8. So this is 8 periodic. And then now you look at the string S1. Okay? Because it is periodic, I can write it in terms of cycle like this. So I use brackets in front at the back. Okay? Sorry, not bracket. I use parenthesis. So saya pakai tanda kurung. It's just to indicate that this is one period. Okay? Now let's consider S1. We start from the front. Okay? You look at every 3 tuples, every 3 strings, 1, 1, 0. You have 1, 1, 0. Next, after that, you have 1, 0, 0. After that, you have 0, 0, 0. Okay? And as you go, you continue, you have all 8 3 strings appears. All of them appears, each one exactly once. Okay? Now, let's start with S2. S2, you have 0, 0, 1. You have 0, 1, 1. And then you have 1, 1, 1, 1, 1, and so on and so forth. Again, each one of them appears exactly one time. Not 2 times, not 0 times, not 3 times, exactly once. Now, if you look closely at S1 and S2, they are actually complement. So if you have 1, you turn it into 0, you have 0, you turn it into 1. So this is complementary sequence. We call them complementary sequences. Okay? So usually you denote them by just a bar on top of. So S1 bar equal to S2. Okay, I'm going very slow here just to make sure everybody get it. Any question about the definition?
Okay, for the participants, maybe you have a question, you can turn your mic on and directly ask Dr. Fred.
Okay, it's important to get the definition. So I hope everybody get the definition, because after this, I'll go a bit faster. So let's look at some of the properties. The first one is it is balanced. So it has the same number of 1 and 0s, which is good for communication, for cryptography. You don't want your adversary to see patterns. Okay, so if there are more ones than 0, then the enemies will see that, okay, so it is skewed, it's not well distributed. But here it is balanced. Why is it balanced? It is balanced because for every string, which we call state, for every state, the complement must also appear. So 110 here, what is the complement? 001. Where is 001 here? So you see, for every state, the complement appears. So no matter how many ones you have, it will be balanced by the zeros on the other side. And of course, the 000 and the 111, they are just their own, they are complements. Okay, so that's the reason why it is balanced. Because for every ones that appears, there will be 0 somewhere that balance it. Okay, and for any positive integer n's, there exist De Bruijn sequences of period to the n. Because usually in mathematics, in combinatorics, you have three basic questions, right? If you define a mathematical object, the first question is, does it exist? You know, you can define mathematical object very, very complicatedly, and it turns out nothing exists there. So then there's nothing to talk about, right? So here, for any given order n, positive integer, you always have De Bruijn sequence. So first, does it exist? Yes. The second question is, how many are there? Then you enumerate them, right? And third, can we build them? All of them? Maybe, if you can, but maybe you want some of them with specific properties. And then you start asking, how do I construct them? The follow-up question is, how can I construct them as efficiently as possible? Right? These are the common questions we have in combinatorics, right? Or in fact, in mathematics in general. So the nice thing is that it can be generated deterministically. I will show you how some method to generate them, but it still satisfies many randomness criteria. I don't want to I don't want to go into too much technical details on what is this randomness, but if you are interested, this is the main reference for signal designs. Okay, so sequences, binary sequences, are usually applied in wireless communication, in radar system, in cryptography. So this is the book to go if you want to look into them. Okay, now the De Bruijn sequence has been known in the literature since 1869. I mean, some people say the Babylonian knows about this, the ancient Indian knows about this, but at least if you trace back the formal appearance in the literature, this comes in 1869. We have a lot of applications, you know, robotic vision, cryptography, DNA sequencing, and even magic card tricks. If you want to look into the overview, okay, I give you there the reference. It's an entire section in Donald Knuth, Art of Computer Programming, Volume 4A. It's a fascinating account of the De Bruijn sequence. Okay, I mentioned to you that for every positive integer n, it exists. The De Bruijn sequence exists. So I'm going to go through you very briefly a proof by math induction. So this is what we call a De Bruijn good graph. Okay, so it was described independently by two persons. One is De Bruijn, the other one is IJ Good. So they don't talk to each other, they don't discuss to each other, and they publish about the same time in two different journals. Okay, so this is quite common in the history of mathematics. People have the same ideas at almost about the same time. So now the graph is known sometimes as De Bruijn graph, sometimes as good graph, sometimes as De Bruijn good graph. It's just that these two are two different people, okay? So now how do you construct this De Bruijn graph? Here, the vertices are all the three strings, okay? So there are 8 of them, right? 1, 2, 3, 4 here, and 1, 2, 3, 4 here. And from every vertex, you have 2 out edge and 2 in edge, 2 in edges and 2 out edges. How are they defined? Look at this 1, 0, 0, 1. So the first 3 comes from 1, 0, 0. And the 1 here comes from the ending here, 1. So you connect this by stringing together 1, 0, 0 and 0, 0, 1. So the common middle term is 0, 0. That's combined. So now you have 1, 0, 0, 1. Okay. So from every vertex, you drop the first entry, and now you keep the last 2. And then you attach either 0 or 1. If you attach 0, it goes into this, through this edge. If you attach 1, it goes through this edge and get into the vertex 0, 0, 1. So I hope it is clear to you how we construct it, okay? So the order is 3 here, and now you construct all of this, okay? All of these vertices. Now the question is, how do you construct the Bruin sequence? Well, you just walk through each of the edge here, making sure that you have an Eulerian cycle. And then you write down the next bit. So from here, let me start from 100, okay? So I will have 1, 0, 0, 1. And then after that, where do I go? Let's say I go here. Then it will be 0, 0, 1, 1. So I attach 1 at the end. So now I have 1, 0, 0, 1, 1. And then I go here. And now I'm adding 0 at the end. So now 1, 0, 0, 1, 0, 0, 1, 1, 0, and so on. So where's the proof? So a de Bruijn sequence, a binary de Bruijn sequence, is an Eulerian cycle because every single 3 string appears. So you must visit all these vertices exactly 1 time. You must visit all of them exactly 1 time. That means you must find in this de Bruijn graph Eulerian cycle. You must identify Eulerian cycle, and 1 Eulerian cycle corresponds to 1 de Bruijn sequence. Okay. So we have this result here. A directed graph has an Eulerian cycle if and only if every vertex in degree equal to out degree. And all vertices with non-zero degree belong to a single strongly connected component. Here we have single strongly connected component. And then look at the in degree and out degree. Out degree 2, in degree 2. So the condition here is satisfied. That means you always have Eulerian cycle. And this is how de Bruijn actually enumerate the number of de Bruijn sequences. Okay, so I hope it is clear to you why we need this this result from graph theory and what's the translation to de Bruijn sequence. Because as you can see here, de Bruijn sequence, we need to visit all vertices exactly once. Okay. And that means we must have an Eulerian cycle. And that's why de Bruijn and I.J. Good, they draw this graph to prove that, well, it satisfies the condition here on the right-hand side, and therefore it contains Eulerian cycle, and therefore it is de Bruijn. So the next question is how many? Obviously, there are many choices here, right? How many? So this theorem 2, there are 2 to the n minus 1 minus n such sequences up to cyclic equivalence. Look at this number. This number is double exponential. The exponent of 2 is also exponential. So what's the point here? The point is that there are so many de Bruijn sequences. You can see here, I'm writing here in the middle here. So the first column here is the order. The second column here is the power of 2. And the last column here is the number of de Bruijn sequences. So you can see here, as the order grows moderately, you already have so many de Bruijn sequences. This is good news because if you have a lot of sequences, then you can accommodate a lot of users, a lot of players, okay? So the proof comes from graph theory, which is well, it's just counting the number of arborescens. I'm not going to go into that, but I list here the references in case you want to see the proof. Okay, so the point from this slide is that there are just a lot of De Bruijn sequences. So they exist. How many? These two questions we already answered. Okay, this one is there exists, and this one is how many. Okay, so we have answered those. Next come, how can we generate them? Okay, so usually there are two yardsticks. If you offer a construction algorithm, the question is, how good are they? How do you define goodness there? Well, the number of constructed sequences and the resources that it takes, you know, the efficiency of construction in time and memory. Can we generate all binary De Bruijn sequences? Yes. The problem is identifying all Eulerian cycle is very memory expensive. Or you can turn it into another problem, which is not memory intensive, but it will take a long time. And sometimes, if you're not a very good programmer or you choose the wrong algorithm, it's both. So expensive in time and memory. So when you look at papers or works or algorithm that say this produced De Bruijn sequences, the first question you ask is, how many? And with what kind of resources? Okay, so now in the next few slides, I will, I think in the next two slides, I will mention a few of the application areas for you to explore. So in cryptography, some De Bruijn sequences, okay, not all De Bruijn sequences, but some De Bruijn sequences can be used as source for pseudorandom numbers and key sequence generators in stream ciphers. So if you read papers in cryptography in stream ciphers and you see De Bruijn sequence, and they are used for these purposes. Okay. Now, which sequences will be good for cryptography? Well, there is an entire area of studies for that. Okay, it's very a very active area. In coding theories, we have implementation of network coding schemes, because if you have a wireless communication, for example, you want to make sure that you know, you have a good network and you have a good coding scheme for that network, so you can communicate well. In robotics nowadays, you know, we have like technologies that will, you know, allow you to write on a tablet or on a computer monitor. This is basically one of the application of the De Bruijn sequence. In robotics, in smart pens, in camera localization, essentially you use the De Bruijn sequence as self-location pattern. If you have hundreds of robots working on the same floor of a factory, you want the robots to know its position, where it is, right? And what is the relation of a robot position to all of the other robots around it? Okay, so we use some form of De Bruijn sequence to tell the robots where you are and how you should move. Okay, it's also a very rich area of studies. This is a paper that I think will be a good gentle introduction to the topic. Okay, now in wireless communication also, some people have looked into using De Bruijn sequences for satellite communications. Actually, the result is not very promising, but still a lot of people are looking into it. Why not very promising? Some of the properties are not so good, but it doesn't stop people from looking into it. Maybe they'll find something good in De Bruijn sequence. Okay, because there are a lot of De Bruijn sequences. So typically for period 1024, where n is 10, there are already a whole lot of binary De Bruijn sequences people can choose from. In bioinformatics and DNA coding, so here I take a screenshot of a paper in 2017 that I work on with Chan Chuling, Johan, and Han Mao here in NTU. We use De Bruijn sequence as a model to design what we call DNA storage. This is an entire different topic altogether. But the idea is, right now we store data, we store our videos, our picture, our music in terms of solid state, right? You have solid state disk, SSD, and all that. Now the idea is, can we store information in the form of protein, in the form of DNA? And we provide some ways of designing them. I mean, this is also a very active area of research, and my colleague Han Mao is one of the leading researchers in this area. So the story behind this paper is that he came to us. Zhang Chuling is visiting me from China at NTU, and we were discussing, and Han Mao happened to be around, and he asked us, do you know if you have a sequence like this with this following property that I can use? And then we immediately says, yes, you can use partial de Bruijn sequences. And we explained to him, and yeah, not too long after we write this paper. So a lot of applications. If you are interested in applications, you're welcome to look into them. And now let's get your paper and pens and computer ready again. Okay, we are going to do some more exercises again here. So I hope all of you have gotten, especially the student, a little bit of abstract algebra, so you know what the polynomial ring over F2 is. Okay, so it's just a collection of polynomials where the coefficients are binary. Okay, the coefficients are 0 and 1s. Now you fix the degree n, let's say 5 or 6. Today we'll try 5. And of course, a polynomial is irreducible if it cannot be factored into two polynomials of smaller degree, strictly smaller degree. So irreducible polynomials, they behave like primes, okay? And some irreducible polynomials are primitive. And if they are primitive, you can use it easily to build an extension field, okay? So how to build an extension field? Usually you take an irreducible polynomial and form a quotient ring. But it's a lot easier if your polynomial is primitive, because then you take the root, and the root generates all the non-zero elements of the extension fields. Okay, so I hope this concept is not very foreign to you, not very new to you. I hope most of you know what the irreducible and primitive intuitively are. So a simple construction comes from, you use a primitive polynomial, okay? So fix the order, choose a primitive polynomial as our characteristic polynomial. Now translate the polynomial into feedback function, and then you choose an arbitrary non-zero state. The state must be non-zero, okay? A state is just a string of length n. Okay, and then now we output what we call an M sequence, or maximal length sequence, and then append a bit 0 in front of the initial state. If you don't understand this completely, that's fine. We'll exercise after this. Okay, so get the pens ready. Now this is a list of 6 primitive polynomials of degree 5, and I'm going to use number 1. Okay, so now here, our state will consist of 5 string. Okay, so binary string of length 5. Now I'm turning this primitive polynomial into feedback function. Look at that. It's very simple. This one, I'm going to write it as x raised to 0, and I equate it to 0. And then because this is binary, plus and minus are the same, I'm moving x squared and x raised to 0 to the other side. And now I'm changing the power into index. I hope it is clear how you translate from one to another. Here, x to the 5 plus x squared plus x raised to 0, it becomes the feedback function. x5 is x0 plus x2. Okay, x5 is x0 plus x2. Now you can do similarly with all the other polynomials, but let's stick with this. So initial state, I'm starting with x0, x1, x2, x3, x4, 5, right? Now I'm choosing a non-zero one. So I'll take a simple one, 0, 0, 0, 0, 1. The one in blue is x0 and x2. You can see that, x0 and x2, these are blue. So now remember the rule, x5 is x0 plus x2. So what is x5? 0 plus 0, because here you have 0 and 0. So that your next bit is 0. That means your next state is you drop the first state, and then now you start 0, 0, 0, 1, and then you append 0 at the end. So this is now 0, 0, 0, 1, 0. Okay? Now, your current state now is the new state here. I'm identifying x0 and x2, 0, 0, 0, 1, 0. So what is the next bit? 0 plus 0. What is my next state? Well, I take the last 4 entry here, 0, 0, 1, 0, and then now I add 0 at the end. Okay? Current state, next state, current state, next state. Just like that. Very simple. Continue all the way until we have a string of length 31. Okay? And then, remember, we still need to add the all zeros. How do you add the all zeros? You put 1 0 in front of the initial state 0, 0, 0, 1 here. So here it is. This is a De Bruijn sequence that you make from this polynomial as a feedback function. So one primitive polynomial gives you one De Bruijn sequence. It's a one-to-one combination. Okay. Another constructions, there are greedy algorithms to do this. So for example, you can start with any non-zero initial state. And then you say, I now prefer 0. So every time I try to append 0, I try to always add zeros. But if it is not possible, I will append 1. Remember, in the De Bruijn sequence, every state must appear exactly once. Every string, every n string must appear exactly once. So if it has already appeared before, you change to the complement. Okay, so you try to always append 0 if possible, otherwise you append 1. But this way is expensive in terms of running time and memory, because every time you are checking if the next state is still possible, you must check back, has it appeared before? If it has appeared before, then you cannot put it there, so you must switch from 0 to 1. Okay, prefer 0 or prefer 1, and here prefer opposite. So if you already have 0 as your last entry, you try to put 1. If you have 1, you try to put 0. Okay, so this greedy approach is typically not very good in terms of memory, but they are easy to describe. So if I'm giving my student a homework, I will usually tell them program this in greedy approach. And then I limit the order to maybe maximum 10, because if I ask for order 25, your computer will stop, will just refuse to count. Okay, so you can read it in this paper if you're interested in, but this greedy approach is interesting for different reasons. Usually people try to look for patterns, so not for speed. Okay, now a method which is very, very good, it's easy to describe, and also it produces a lot of sequences. This is what we call a cycle joining method. For cycle joining method, your polynomial doesn't have to be primitive. It doesn't even have to be irreducible. You can have product of irreducibles, and then you can still apply this cycle joining method. There are only a requirement that your polynomial must not end in 0 here. So the coefficients of x raised to 0 must be 1. Okay, but this is the only requirement. Now, if you have this polynomial, for example, okay, then you can turn it into feedback function as usual. You equate it to 0. You move x cubed plus x squared plus x raised to 0 to the right-hand side. Of course, it doesn't change sign because plus and minus is the same in binary. And you turn it into feedback function. And now you produce cycles. If you start with 0, 0, 0, 0, 0, you have you keep going from 0 to 0 to 0 to 0. So this is one cycle. Okay, and then now you take another state which is not in the first cycle and you produce the next state, the next state, the next state using this feedback functions. So now you have these cycles. You have C0, C1, C2, C3. Look at the name of the method. It's a cycle joining. So cycle joining, essentially, if you produce cycles, now you try to join them. And if you notice, I put orange color here and blue color here between C1 and C2, and the red one between C1 and C3 here. So I'm going to use the states with the same color to connect the cycles into one big cycles. The final product will be binary De Bruijn sequence. Okay. Now, look at the cycles with the same color. These are the head of the cycles, the heads of the states. You know, these states are called conjugate pair, because if you look at the head, they are complementary. So here 0 and that is 1, here 0 and that is 1. The tails are the same. Okay, and if you have a conjugate pair like that, one element of the pair is in one cycle, the other element is in another cycle, then you can combine this. And this is called the cycle joining method. So essentially, after this first blue state here, you don't go into 1100, you go to the next state after the pair. So from 0110, I go into this 1101, and I continue following C2 until I reach 1110, and then from there, I jump to C1. My next state is 1100. Okay, so that I combine C1 and C2. So this is how you do conjugate pair. I can join C0 and C1 based on this pair. Okay, so after 1000, I go to 0001, and then from here I go back to 0001. So I put 000 between 1000 and 0001. Okay, so I combine C0, C1, and then I combine C2 and C. Join C2 and the resulting result of this process, I join them using the blue pair. Again, I join C0 and C1 using the orange. I have this as a result, a longer cycle. And now I'm joining that longer cycle using connection between C1 and C2 using this conjugate pair. Okay, so I'm combining them. And then in the end, I combine the result with the red partner here. Okay, then I can combine them. And I get the De Bruijn sequence at the end. So your question is this the only way? No, not really. There are many ways of combining these cycles. You can probably identify here 11110. Do you have 0111? It's here, so you cannot combine it using that one. But maybe there are others. Okay, so there are many other ways of joining the cycles. Now, as I mentioned, this is the most comprehensive work on how to join these cycles. Okay, so if you want to look into what is the state of the art, this is the paper to go. And now I'm going to discuss here, finally, the successor rules, which is the content of the main reference paper. I hope I haven't lost most of you at this point. Okay?
Yes.
So,
sorry, Dr.
yeah.
Fred, we have 5 more minutes for the presentation. Okay.
No problem.
Thank
Okay.
you.
So we have the cycle joining method, right? And now, a successor rule is a special form of cycle joining method. You want to quickly identify how to pair your cycles without checking every time you don't want to check, okay, how to pair this with the next one. So what do? So you identify feedback functions that produce many short cycles, because if you have many short cycles, it doesn't take long to identify a specific cycle in every, a specific state in every cycle. And it will be nice if the feedback function gives you some ideas of what properties do they have. Okay, so you come up with a function, a feedback function that give you many cycles. And then you want these cycles to have properties that you can pinpoint. I will use you, I will use you, I will use you in each cycle. We call it as a reference state. And then you want to now establish a rule how to pair a reference state or some state with respect to that reference state into another state, so that you can do cycle joining method, but faster. Okay, so for this paper, the main reference paper, we use this feedback functions. We call it PRR, pure run length register. Okay, so the feedback function is just like this. It's very simple. It produces a lot of short cycles. Okay, the paper has the proof on the properties and how many they are and so on. So it produced two types of cycles. One is a pure cycling and another what we call a complemented cycling. And the pure cycling follows this rule, very simple rule. And the complemented cycle follows this rule, which is also very simple. And then what is the reference state? The reference state, we usually choose the necklace, which is the least lexicographically state, the least lexicographical state in the cycle. And then we choose the co-necklace. Co-necklace is just the complement of the necklace. Okay, so we have feedback function that produce a lot of short cycles. And these cycles, we identify the necklace and co-necklace. And because they are of two types only, okay, then you can easily say, okay, how you connect one to the other. So this is an example with n equal to 6. This script P is the pure cycling. And the script C is the other type, the complemented cycling. Okay, you can reproduce this yourself later if you are interested and you have the time. So we have 8 cycles of the pure cycling type and 4 cycles of the complemented cycling type. And you can identify the necklaces. And because you can identify the necklaces, you can order the cycles according to that type. Okay, so the blue ones here are for the C1 until C4. The rest are for P1 until P8. So now you have your reference state. Then you can define the rules. So this is a typical route to connect all of the cycles. So for this special example, this is the connections that we make. Okay, but in the paper, we identify 4 different classes of assignments that you can use quickly. Okay, and the rules we have identified, they are fast and they can produce, they're not many, but not so bad as well. They're exponential. Remember, when you use primitive polynomial, for every one polynomial, you get one de Bruijn sequence. Here, for every n, you get 2 raised to the n minus 3. So for example, if your n is 3, then too bad, you have 1 only. But if your n is 8, for example, you have 32. Okay, so now let's take a look at the program. So the program goes like this. It's designed, okay, you can check the C program, but if I run it, it will first ask you what's your order. So let's say I put order 8. Order 8, that means the length is 1024 divided by 4, 256. So each sequence will be 256. That's a lot. So probably this is too much. I will put maybe 6. You see, it's very fast, right? You know, blink, it comes out. And it can handle up to, for example, I use, I don't know, 12. Let's see. Keep producing. Okay, let me stop it. So depending on how many you want, you can produce. But of course, our promise is that it will be fast, then it will produce quite a large number. Okay, so thank you very much for your kind attention. And now I'm entertaining questions if there are. Thank you.
Okay, thank you, Dr. Martianus Frederick Ezerma, for giving us such informative and interesting presentation about the Bruin sequence, right? Okay, so ladies and gentlemen, now we come to the question and answer session. If I check in the column Zoom, there are no questions, so maybe there is one or two of you who want to ask directly to Dr. Fred Ezerman. You can turn your mic on and begin to speak. Is there anyone?
You don't have to worry about using English. I understand Japanese and Bahasa Indonesia well. So or you want, you can also ask in French, but my French is not so good anymore now. So you can ask in Japanese or in Bahasa Indonesia.
Yes.
Okay.
Okay, is there any question maybe from the students? Maybe who have interest in the Bruin sequence, maybe who want to take the undergraduate research in these topics, you can ask. Okay. So, Dr. Fred, if I'm not mistaken, in the cryptography, one of the aspects that we need to consider is about the randomness, and you also mentioned it before in the Bruin sequence. It satisfies some randomness criteria, and
yes,
I ever read an article that one of the good randomness criteria is because this De Bruin sequence can be generated from nonlinear feedback shift register, right?
Indeed.
Yeah, so compared to the method that you have already mentioned in this presentation, maybe you can give some maybe a bit about the how to produce this sequence from using nonlinear feedback shift register, or maybe you can start from the when we produce using primitive polynomial, we start with the feedback function right now. So maybe you can give some connection with.
Okay, I'll try to explain briefly by some examples. Okay. I think I will choose this particular paper because if you look at the authors, right? Janusz is joining us for this paper. Janusz is at the Military Communication Institute in Poland, and his specialty is really to try to get the Bruin sequences or related sequences with good cryptographic properties. So the one that I show you using this easiest construction using primitive polynomial is worse for cryptography. You should not use this because this is so easy to guess. This is completely trivial to guess. So don't use simple polynomials like this for cryptography. Okay, so as you have remarked, we need to have sequence with high nonlinearity. In fact, that is the topic of research that Pak Mustafa is doing right now. So he's trying to identify modified De Bruin sequences with the largest nonlinear degree. So we are making good progress in that. Hopefully it will get into something useful. So when you apply cycle joining method, that is where you change the linearity profile. Because if the more you apply the cycle joining, the more nonlinear they can get. But if you are looking into something which is more for cryptographic purposes, then this is the paper that explain a bit on it. Because here what we use yeah, sorry. Here in the cross joining, we use another topic. So we use Zec logarithm, which is a tool in finite field theory to apply to cycle joining, and another method we call cross joining. So in the cross joining pair, the result will be a lot more nonlinear. So if you look at this one, right, these are the resulting ones. You can see it is a lot more nonlinear. So a few prototype of a security system for passport for European unions, they use some of these sequences. The length is, I think, 2⁻12, which is 4096. So the security system for some of the EU passport uses some variants of the Brin sequence. So what Janusz and some of his colleagues in Poland are doing, they are looking at the following sequence. They are looking at the Brin sequence where all the terms are linear until the last term. And in the last term, you have a very highly nonlinear term. So why do you want that combination? You want most of them to be linear because when you build a chip for passport, right, the chip cannot be too big. It cannot be too heavy. It cannot be that because it will make it expensive, and it will make it that you need to construct the reader from a very specific power constraint. You don't want your passport to be too complicated to read. So they try to identify that. So of course, in cryptography, you want combinations of high nonlinearity, but also from the perspective of the designer, it cannot be so difficult to construct.
Yes.
Yeah. So you want to know how to construct it quickly, but for your adversary, for people who try to hack into the security system of the passport, it will be very difficult. So that kind of combinations, I think we explain it a little bit here. I'm not sure how much of it will be of interest to most of you, but if you are interested in this, here is the source to look into. This paper is available openly. This is an open access paper. So we also have the software implementation here. As you can see, complete software implementation, and you can see that's the graph. One of the graph looks quite scary. Where is it? So some of this formula also come from British security agency, but here it is. So you see, this is the adjacency graph, and to build the Brin sequence, we choose one spanning tree from here.
Okay.
This is how it will make it very difficult for your opponent, for the hackers, to know which one. But we, as the designer, we will keep this in encrypted memory form. Yeah. So if you're interested on that, we have this software implementation here, and how to do it. So maybe for students who want to do some final year program project, you can choose some of the simple ones. Okay, not a very high order, but this should be interesting enough for an undergraduate project. So thank you. I hope that answers it.
Yes. Okay, thank you. So maybe this is like something when in the SIMS in 2019, that's the first time I see that coding theory and cryptography can be combined using code-based cryptography, right? When we encrypt the message using the coding theory, so that our opponent will be confused because there is an error in the encryption. So it will be something like that. Yeah. Okay. Thank you, Dr.
Thank you very much.
Yes. And
stop sharing. Thanks.
There is one more question from our chairman of conference.
Oh, okay.
Mr. Muhammad Hafiz, please.
Ya, saya gunakan bahasa Indonesia saja, Pak.
Oh, silakan.
Ya, terima kasih Pak Fred, sangat menarik presentasinya. Saya tertarik ini Pak Fred. A lot of application domain including robotic vision.
Ya.
Setahu saya itu Pak Fred, kalau saya kan tidak di domainnya jenengan. Robotic vision itu artinya kalau kita melihat gambar itu kan robot itu mengartikannya berupa angka gitu Pak Fred. Nah, sedangkan yang di De Bruin itu angka-angkanya yang ada itu 0 dan 1. Artinya apakah gambar yang diterima oleh robot ini tuh dikonvert terlebih dahulu ke hitam putih. Kalau 01 kan biasanya identik dengan hitam putih. Itu yang pertanyaan pertama Pak Fred.
Ya.
Sedangkan di gambar sebenarnya itu kan bisa tergantung RGB atau apanya itu Pak Fred.
Ya, betul.
Pertanyaan kedua itu cycle-nya itu efek cycle di situ seperti apa nggih Pak Fred? Saya masih belum ada gambaran mengenai aplikasi cycle-nya di robotic vision ini Pak Fred. Itu saja Pak. Terima kasih banyak.
Terima kasih. Saya jawab dalam bahasa Indonesia juga ya.
Oke.
Biasanya, saya ambil contoh yang sederhana aja. Ini saya pakai tablet. Tablet ini kan ada pensilnya. Nah, kalau saya mau menulis di tablet ini, pensil ini perlu pertama kali tahu dia lokasinya di mana. Lokasinya di layar ini ada di mana. Nah, yang dilihat oleh sensor yang di ujung pensil ini adalah pola yang ada di range of vision-nya dia. Dia bisa lihat entah betul pakai kamera, ada beberapa pensil yang pakai kamera, atau pakai sensor elektronik. Jadi di layar ini yang lebih panjang ini pakai De Bruin sequence, yang tingginya ini yang dimensinya kurang dari panjangnya ini pakai half De Bruin sequence. Jadi pensil ini tahu persis dia berada di mana. Nah, ada error correcting capability-nya. Jadi misalnya layarnya ini kotor karena kena sidik jari atau kena debu. Dia masih bisa mengenali dari error correcting property itu posisi saya di mana. Jadi lebih vision dalam arti orientasi. Dia tahu, dia membaca entah dari sentuhan elektronis ini dia bisa baca, atau ada yang ada kameranya, dia bisa baca lokasi saya di mana relatif terhadap layar ini. Kemudian kalau kita bicara tentang automated workers gitu ya, robot yang ada di lantai produksi gitu. Mereka perlu tahu kalau saya bergerak ke sana nanti saya nabrak apa enggak. Kalau saya geser ke sini, robot mana yang ada di proximity saya. Itu kan komunikasinya pakai sensor, kadang pakai optik, kadang pakai wireless command gitu ya, pakai gelombang. Jadi vision ini bukan hanya dalam arti dia melihat sesuatu, tapi dia merasakan sesuatu, dia sensing sesuatu. Nah, paper yang saya sebut di sini, Simple and Robust ini sebetulnya sederhana karena dia hanya 4 halaman dan dia menjelaskan bagaimana caranya bekerja pada layar screen yang seperti ini, touch screen dan sebagainya. Sekarang sudah ada yang jauh lebih sophisticated metodenya, itu dia bisa multidimensi. Nah, ini salah satu bab di buku yang sedang saya edit ini, ditulis oleh orang-orang yang memang ahli ini, 4 orang. Jadi nanti satu bab di situ khusus tentang robotic vision position locator ini. Kurang lebih itu salah satu aplikasinya. Itu, Pak. Terima kasih.
Terima kasih banyak Pak Fred.
Okay, so I'll be back using English.
Sure.
Okay, so unfortunately our time is limited. So for any other participants who want to ask more about the topic from Dr. Martianus, you can contact him in his email or visit his personal webpage that already be mentioned. And also I have posted the slide in the column chat. So you can access it, and if you forget about the address of the personal webpage, you can also access it in that presentation. So, ladies and gentlemen, we finally arrived at the end of the first plenary session of ECOMET 2021. We would like to say thank you again, especially to Dr. Martianus Frederick Ezerman for his informative, interesting presentation, especially this with the topic that is very close to our daily life, our technology that is maybe beside us when we start open our eyes, we see the our smartphone with the touchscreen and so on. It is very close to that topic, and that's very interesting. And also we want to say thank you to all of the audience, and hopefully the presentation will be beneficial for everyone. So at last, thank you for everyone. Good morning. Assalamualaikum warahmatullahi wabarakatuh, and I will pass the time back to our MC, Ms. Rahmati. Thank you. Thank you, Dr. Fred.
Thank you.
Most welcome.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you so much, Mr. Muhammad Agung. And ladies and gentlemen, once again, virtual clap for Mr. Fred Ezerman. It's a very informative and interesting presentation. Well, next we're going to proceed to the second plenary session. Would like to invite Mr. Darmawan Setyananda, STMT, as the moderator. And we're going to listen to a presentation delivered by Professor Dr. Toto Nusantara from Universitas Negeri Malang, Indonesia. Well, Mr. Darmawan Setyananda, over to you.
Yeah, thank you. For the next session, for the second speaker, we will have a presentation from Professor Toto Nusantara. Before that, I am Darmawan Setyananda, and I'm a moderator of this second plenary session. It's glad to see you all here and welcome to this session. Professor Toto Nusantara will present a paper or article entitled Regular Property Preserved on the Product of Anti-Fuzzy Graph Cycle. And before we get started, I will read a brief biography of our distinguished speaker today. I will share the CV of Professor Toto. Okay. Yes. Yeah. Professor Toto Nusantara currently is a professor in Mathematics Department, Universitas Negeri Malang. And he has academic qualification from IKIP Malang as a Sarjana Pendidikan, and then a master degree from Institut Teknologi Bandung, and as well as the doctoral degree from ITB also. His research fields is about dynamic system and anti-fuzzy graph theory. Besides research, he also has academic or administrative experience as a head of mathematics department and chairman of LP2M, or Center for Research and Center of Research in Universitas Negeri Malang. And he also published some articles in journals or proceedings. And one book about system dynamic linear was written by Professor Toto Nusantara. For the rules of this plenary session, the presentation will be performed in 40 minutes. And after it is finished, we will have a Q&A session for about 20 minutes. If the audience have a question about this topic, please write down your comment or question in chat box of this Zoom meeting, and I will deliver to Professor Toto Nusantara. Now allow me to welcome to the speaker, Professor Toto Nusantara, to deliver his presentation. Professor, the floor is yours.
Okay, thank you, Mr. Darmawan, for the time. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, the Honorable Invited Speaker, Conference Committee, invitees, and conference participants. I'm grateful to be given an extraordinary opportunity to present in front of all of you. And for Pak Pur, permisi Pak Pur, and also Pak Surahmat, because I would like to present about the graph theory that you are all of the master in the graph theory. In this happy morning, I would like to present about the interesting and relatively new topic, namely study in anti-fuzzy graph. And Pak Darmawan, today I asked the committee to present my presentation.
Oh, or
Pak Hafiz, I think I already gave a.
Okay. Okay. To the operator.
Okay. Okay. The title of my presentation is about the regular preserve property on the product of anti-fuzzy graph cycles. My name is Toto Nusantara. I'm from the Mathematics Department, Universitas Negeri Malang. Okay, next presentation, please. Okay. The organization of my presentation is as follows. The first, I would like to introduction and background of the problem and the motivation of the discussion. And the second part is about the explanation of a specific term that I use in this discussion. And the third is I'm going to describe the definition of what is the meaning of regular anti-fuzzy graph and some of these properties. And the fourth part is the main result. This is the core of the discussion. That is how to construct an anti-fuzzy graph with a larger size, but still retaining the regular properties of its component. And the last presentation is about the conclusion. Next. Okay, next. Okay. And a new trend in graph theory that is lead to the use of a fuzzy coefficient both in the vertex and edge coefficient. Why? Because it is makes sense in the fact that we cannot represent the parameter or the coefficient in vertex or in the edge of graph to be integer, as in the case of a communication network that often been discussed in the graph theory. The ring power, the receiver power, and the transmitter quantity in the real unit. So it makes more sense if the study leans towards fuzzy graph. And also, like we say in the social network, analysis is currently developing rapidly. The use of a fuzzy and fuzzy graph is more reasonable. Quite a lot of study that talk about this analysis. Next, about the fuzzy graph. This is a relatively new field. After Zadeh in 1965 introduced about the fuzzy theory, and then followed by Kaufman and Rosenfeld in 1975 that introduced about the fuzzy graph. After that, the new horizon of a fuzzy graph study began to develop rapidly and keep pace with the recent development in graph theory. And next, in 1912, Akram look at the other side of the study of fuzzy graph. That is by change the existing relation in vertex and edge and found new structure of a fuzzy graph. This is, of course, as a complement of the fuzzy graph studies that have carried out so far. Next. Okay. The anti-fuzzy graph that we already have to study. We have some papers, several results for in the anti-fuzzy graph, starting at 2019. There is a 7 article have been produced. Most of them is discussed about the regular properties and also about the bipolar or magic or anti-fuzzy line graph that we already resulted in this study. Okay, next. Okay, now we come to our discussion. What is the problem? When we have two anti-fuzzy graph, and then we want to produce a new anti-fuzzy graph that's more larger than the previously. In this case, we are going to use a cycle. We have two anti-fuzzy cycle, and then we combine two cycle with the anti-fuzzy graph product, and the result is anti-fuzzy graph also. But the question is, if we start with a regular cycle, both of them, could the regular properties of the component still preserve in the new product? This is the question of our study. And the second question is, this product should be larger size than the previous component. For example, we have in this case we have the size of cycle, and then the next product should be larger than the size of sum of both cycles. Okay, next. Okay, we start with the basic definition. Basically, that what we have studied is part of the graph theory, especially when we see or we study about the graph labeling. Fuzzy graph or anti-fuzzy graph is a part of graph labeling. But the difference is how to define the relation between vertex and edge in here. For fuzzy graph, the relation between edge and vertex, the degree membership of edge should be less than minimum of the degree membership of this vertex. But in the contrary, in the anti-fuzzy graph, we have the relation that the degree membership of this edge of the graph is larger than maximum of the degree membership of their vertex. Okay. Next. Next, please. Okay. Okay. We have already present the definition of the anti-fuzzy graph. It's mean that if we have a set of T, there is a set of this vertex phi, and we have also relation sigma is the degree membership of this vertex, and mu is the degree membership of this edge, and we have the relation that the for each edge UV, the degree membership of UV is larger than the maximum of the degree membership of edge phi and degree membership of phi. We also introduce about the degree of vertex. What is the meaning of the degree membership, degree of vertex? The degree of vertex is sigma of the degree of edge that connected to this vertex. For example, if we have in here the degree membership of mu1 is the degree membership of mu is equal to the degree sigma of mu1 mu2 plus mu1 mu5 mu1 mu3. So if we consider the degree membership of mu4, we already have in here the number is 1.6 for a 1.9, and we also define about the total degree of vertex. If we add the degree of vertex plus the degree of this vertex, this called as the total degree of vertex. In this example, if we consider to vertex mu2, we have in here that the total degree of mu2 is equal to 1.7. It's obtained from the degree membership of mu2, mu1, mu2, mu4. That is 1.65 plus 1.55 plus 1.5. So we have a 1.7. And we need one more definition is about the size of anti-fuzzy graph. That is defined as the sum of all of edge of graph. It means size of T is equal to sum of mu u phi, where mu u and phi element of phi cross phi in here. For example, in here that the size of graph G1 is equal to 4.8. It's obtained from the sum of this edge 1.65, 1.45 plus 1.65 and etc. in here, and we can find the size of G1 is 4.8. Next. Okay. The next definition is about the, if we try to find the minimum of degree, the minimum degree vertex G is if we try to count the degree of all of vertex and then try to find the minimum of them, and then we call as minimum degree is minimum of degree of each vertex, and the total minimum degree of vertex G is minimum of the total degree of each vertex of this graph G. And we also define the maximum of degree. Is mean if we consider to the maximum of the degree of vertex, all of the vertex, and then find the maximum. And the antifasy graph G to be P vertex regular if the minimum degree vertex of G is equal to maximum degree of vertex G. This means with the number P, and if we have the number minimum total degree of G is equal to maximum the total degree of G, then we have the definition of a key total vertex regular of the graph G. In this example, we have a G2. In here, we can account that the minimum degree of G is equal to 1.8, and also the maximum degree of G is 1.8, and we can conclude that this antifasy graph is 1.8 vertex regular. And we also find that the total degree of this antifasy graph is minimum is 2.2 and the maximum is 2.22. And in this case, we have this kind of graph, this kind of antifasy graph is 2.2 total vertex regular. Okay, next. Okay. Next is about the definition of the graph structure that we are going to use in this discussion. First, the definition of path. As in the graph theory, path is defined as the sequence V1, V2 until Vn with the n positive. And we add the property because we consider the antifasy graph that satisfy that mu vi vi plus 1 is larger than sigma vi, maximum of sigma vi and sigma vi plus 1. And from this definition, we already have that every path in the case is 2 is P2 path can be so that this P2 is a vertex regular for every P2. And if we consider to the G in general, that the G is an antifasy graph, then every vertex, if we take a mu v element h, we also have that every edge is a vertex regular. So basically, that antifasy graph is a compound of the vertex regular. And the next is about the cycle. Cycle can be defined as a path, but in the last of is V1 is equal to Vn for n larger than 3. And the properties of cycle, if we consider that mu is a constant, then we have that this cycle to be vertex regular. For example, if every mu I element of a cycle n is equal to k, and then we have that the degree of mu I is equal to k. Hence, the Cn is 2k vertex regular, both in n even or odd. But if we consider the mu I mu equals 1 is k2, and mu I minus 1 mu I is equal to k1 to be alternate, then every I with n is even, then the degree of mu I is equal to k1 plus k2. So Cn with n even is k1 plus k2 vertex regular. And we can also show that for every cycle n, then the size of this cycle is equal to half n times the k of the number of degree of membership of vertex. Okay, next. Okay, we come to the main result. Okay, next. Okay, first we talk about the Cartesian product. What is the meaning of a Cartesian product in here? This definition is actually we adopt from definition in the fuzzy graph, but we modify in degree membership of this vertex. For fuzzy graph, the definition is taking to be minimum of sigma mu, sigma 1 mu, and sigma 2 phi. But for anti-fuzzy, we define as a maximum of sigma 1 mu and sigma 2 phi. And for the edge, we define as follow. We have two properties in here, that every edge in here, we define if mu1 is equal to mu2 and phi1, phi2 element in edge of the second graph, we define the membership is equal to sigma 1 and sigma 1 phi1 maximum with mu2 phi1 phi2 and etc. in here. And if we consider the graph of a cycle, for example, we take a C4 and a C3 in here, then the Cartesian product produce anti-fuzzy graph also. We can prove it if we consider two anti-fuzzy cycle C3 and anti-fuzzy cycle C4, and we produce a new anti-fuzzy graph in the right-hand side in here. But it is interesting when we consider the parameter of degree of membership in vertex and degree membership of the edge. That is, if sigma 1 is less than the degree membership of edge in second graph, and the degree membership of vertex sigma 2 less than the degree membership of edge in the first graph, then we found that the Cartesian product Cn cross Cm cross Cn is to be K1 plus K2 vertex regular anti-fuzzy graph. So if we consider first the component is K1 vertex regular Cm, and the second also K2 vertex regular Cn. With this condition, we found that the Cartesian product of both of them also produce a anti-fuzzy graph in the form of a vertex regular anti-fuzzy graph. And if we identify that every point in CM cross CN for every every U and phi in CM cross CN is have a 4 neighbor. For example, in here we have a 4 neighbor, so we can see in here that the size of this product is equal to half of M, that is the number of vertices of the first cycle, times N, the number vertices of the second cycle graph, times K1 plus K2. And also in this case, this product also commutative. It means that if we consider GM cross GN is the same as the cross product of GN cross GM, which is K1 plus K2 vertex regular anti-fuzzy graph, and the size is also the same as I mentioned it. Next. And if we try to make it soft sufficient condition, for example, in here, if we consider first is a anti-fuzzy graph cycle K1 vertex regular CM, and the second is also anti-fuzzy graph cycle with a K2 vertex regular CN. If the condition, the degree membership of the first graph, the degree membership of the vertices of the first graph is equal to the degree membership of the vertices of the second graph, which is constant, and still satisfy the previous condition, we obtain here that the Cartesian product is not only vertex regular, but it's also a total vertex regular anti-fuzzy graph. And the second result is, the third result is when we take both of the condition, which is if we take the degree membership the first vertex of first anti-fuzzy graph CM is equal to the second membership of vertex CN, and also the degree membership of H first CM, and same as the second degree of H of the second graph, and the condition of still satisfy sigma 1 is less than the mu2 and sigma 2 is less than the mu1, then we found that this is not only vertex regular, but we found that the product is also edge regular. Edge regular with the coefficient K1 plus K2 as regular anti-fuzzy graph. And also the product CM cross CN is also K1 plus K2 total edge regular anti-fuzzy graph. This is the third result in the Cartesian product. Next. Okay. The second product that we consider in here is a composition product. For two graph, we compose it with the definition in definition 10 in here. It means that for vertex, we define as the previous product, still as a maximum of the first vertex sigma 1 and the second vertex of sigma 2. But in the edge, we define more complicated in here. So with this definition, if we consider two cycle, for example, in here C4 antifasi graph C4 and C3 antifasi cycle with 3 vertices. This product resulted more complicated product of antifasi graph. We can show that the composition of C4 to C3 is antifasi graph also. But the question is, if we consider first is regular, C4 regular, and then C3 is also regular, can we find that the product is also regular? This is the first question. And the second question is, if we consider composition of C4 next to C3 is the same as the composition of C3 next to composition of C4. This is two questions that arise from this composition. Next, for composition product, we found that if we consider first K1 vertex regular GM, and the second is CN K2 vertex regular, if the condition that the membership of the vertex first graph is less than the degree membership of the edge of the second graph, and the degree membership of the second vertex is less than the degree membership of the first edge, first graph, then we found that the composition of GN next to CN is N is the number of vertices of the second graph times the K1 is the degree of G1 plus K2, the degree of the second graph. That is, the composition is N K1 plus K2 vertex regular antifasi graph. So we found that this property from the component, the constituent component, because we consider to regular, the component is regular, then we found the product is also vertex regular antifasi graph. And for every vertex in product CN next to CN, we found 2 times 1 plus N Nickboard. And if we try to account the size of the graph is equal to M times N composition to 2 plus 2N times the degree of product graph, which is N times K1 plus K2. But if we consider to different arrangement, for example, if we consider to CN next to GN, composition of two graph, then we found that the number of degree of product is different from the previous, which is M times K2 plus K1 vertex regular. So the composition product in here is not commutative as the previous. Next. Okay, this is the last product that we consider to see, namely direct product. The direct product of two antifasi graph is defined as follow. Is for vertices the same as the previous product, but we differ in here in the definition of edge. This edge is defined as mu mu of mu direct product of mu1 v1 mu2 v2 is equal to mu1 mu1 mu, which is a maximum of a degree of first X and maximum degree of the second graph. For example, in here, if we consider two direct product of cycle with the 3-point antiphasy, and we found also the product is a larger size than the constituent. And the interesting question is, if we consider to G1, G2 as a regular, is the product is also regular. And this is the last of our theorem in here. And we can show in here that every vertex in product has m-1 times n-1 network. And the last theorem, next. Okay. The last theorem, we found here that direct product of G1 as a GM of K1 vertex regular of a cycle with the point of M, and G2 is antiphasy graph of K2 vertex regular of a cycle with the number of vertices of N. Then if M and N odds, only we consider only odds, and K1 is less than K2, then the direct product of two cycle is m-1 times m-1 K2 vertex regular. And if M and N is odd and K2 less than K1, then the direct product of two cycle, Gm and Gn, is m-1 times n-1 K1, we change because K1 is larger than K2, vertex regular antiphasy graph. And the size of this product is equal to a combination between number m times n with the m-1 times n-1, and we can choose the maximum of the degree of vertex K or K1 or K2. This is the last our presentation about the result in the how we construct a new antiphasy graph that preserve the property of the component. Next, the conclusion. Potentially, antiphasy graph product can be found that produce a new graph with the basic property in the constituent. In our case and our discussion, we only consider to the regular properties, and still a lot of properties that we can discuss in here. And this result can be extended to be more complex graph shapes, because we consider only on the cycle. Maybe we can look at the tree, forest, or on the complete graph and etc. in here. Okay, I think this is end of my presentation. Thank you very much.
Thank you for Professor Toto Nusantara for the informative and valuable presentation. And now we come to the Q&A session. If the audience have a question or comment, please write down your question in chat box in this meeting. And do not forget to write your name and your institution. It looks like up to now no one submit a question.
Okay, maybe to be more lebih mudah mungkin.
Oh,
materinya terlalu mudah.
or perhaps if the audience wants to ask directly, the audience can submit email to Professor Toto at email address toto.nusantara.fmipa@um.ac.id.
Okay, ada tanya.
Okay. You want to close the session, Professor? Nobody asked.
Okay, terima kasih.
Okay. And ladies and gentlemen, finally we come to the end of the session, and I would like to thanks to Professor Toto for the valuable presentation, and I hope the audience get insight, get valuable, beneficial knowledge for all of us. All applause is for the speaker and the audience. Thank you very much, and wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam
warahmatullahi wabarakatuh. Thank you so much, Mr. Darmawan. And once again, let's give a big hand for Mr. Toto Nusantara for the very comprehensive and insightful presentation. Well, ladies and gentlemen, before we proceed to the next plenary session, the last plenary session for today, we're going to have a break until 12 o'clock, 12 sharp. So we're going to have about 10 minutes break. And while we're having a break, the operator will play some songs for us. Okay, let's have a break and see you in 10 minutes.
It's here with us again.
Yeah, come on.
What? It's a CAKRAWALA.
Malang State University. People say that the world won't orbit around you, 'cause it's so hard to look up when you're feeling down.
Ain't nothing in this world, paper just how you like it. So don't stop, won't stop till you make yourself proud. Just keep on moving, nothing's gonna stop us now. Let's prepare our future, nothing's gonna wait. Let's make our way brighter, gotta let it shine. We'll be up in the sky.
Come on, baby, stand inside my world. See how now we're turning and won't stop. 'Cause we ain't dreaming, we make it real. It's time to make a change.
See, you're trying to get the number one, but don't forget what you want. Keep your hope high, make every time count. Get that confidence build up and know what you are for. There'll be bumps on your way, 'cause perfection is so quick to pour. Nothing's gonna do it if we ain't. The art of achieving is when we are learning all day, learning all night. We'll shine and you'll see me right. Just keep on moving. Nothing's gonna stop us now. Let's prepare our future. Nothing's gonna wait. Let's make our way brighter. Gotta let it shine. We'll be up in the sky.
As the world keep moving, people will always keep changing. So stop daydreaming about your broken heart. Set your goal up high, then you'll see the light shining brighter than the sun.
Let's clap together and sing along. Come on, baby.
Step inside my world. See how now we're turning and won't stop. 'Cause we ain't dreaming, we make it real.
It's time to make a change. Come on, baby.
Come on, baby. Step inside my world. See how now we're turning and won't stop. 'Cause we ain't dreaming, we make it real.
It's time to make a change.
Come on, baby. Step inside my world. See how now we're turning and won't stop. 'Cause we ain't dreaming, we make it real.
It's time to make a change. It's time to make a change. Come on, baby. It's here with us again.
Yeah, come on.
What? It's a CAKRAWALA.
Mindset University. People say that the world won't orbit around you. 'Cause it's so hard to look up when you're feeling down.
Ain't nothing in this world, paper just how you like it. So don't stop, won't stop till you make yourself proud. Just keep on moving. Nothing's gonna stop us now. Let's prepare our future. Nothing's gonna wait. Let's make our way brighter. Gotta let it shine. We'll be up in the sky.
Come on, baby. Step inside my world. See how now we're turning and won't stop. 'Cause we ain't dreaming, we make it real.
It's time to make a change. See, you're trying to get the number one, but don't forget what you want. Keep your hope high, make every time count. Get that confidence build up and know what you are for. There'll be bumps on your way, 'cause perfection is so quick to pour. Nothing's gonna do it if we ain't. The art of achieving is when we are learning all day, learning all night. We'll shine, and you'll see me right. Just keep on moving. Nothing's gonna stop us now. Let's prepare our future. Nothing's gonna wait. Let's make our way brighter. Gotta let it shine. We'll be up in the sky.
As the world keep moving, people will always keep changing. So stop daydreaming about your broken heart.
make it real. It's time to make a change. Come on, baby.
Come on, baby. Step inside my world. See how now we're turning and won't stop. 'Cause we ain't dreaming, we make it real. It's time to make a change. Come on, baby. Step inside my world. See how now we're turning and won't stop. 'Cause we ain't dreaming, we make it real. It's time to make a change.
It's time to make a change. Come on, baby. It's here with us again.
Yeah, come on.
What?
It's a CAKRAWALA. Mount State University. People say that the world won't orbit around you. 'Cause it's so hard to look up when you're feeling down.
Ain't nothing in this world, paper, just how you like it. So don't stop, won't stop till you make yourself proud. Now just keep on moving. Nothing's gonna stop us now. Let's prepare our future. Nothing's gonna wait. Let's make our way brighter. Gotta let it shine. We'll be up in the sky.
Come on, baby. Step inside my world. See how now we're turning and won't stop. 'Cause we ain't dreaming, we make it real. It's time to make a change.
See you trying to get the number one, but don't forget what you want. Keep your hope high, make every time count. Get that confidence build up and know what you are for. There'll be bumps on your way, 'cause perfection is so quick to bore. Nothing's gonna do it if we ain't. The art of achieving is when we are.
Hello, Marco. Good
Hello.
morning.
Good morning. Can you hear me?
Yes, yes.
Okay.
Nice to meet you, Marco.
Likewise, finally.
How are you doing, Marco?
I'm well. I'm well, thanks.
Good. Okay. Yes.
Okay. Yeah. Let me say hi to the audience first because we just have a 10 minutes break, Marco. Welcome.
Yeah. I heard the song.
Yeah, it's a nice song. Thanks. Hi, everyone. Welcome back. I hope that you're refreshed after the 10 minutes break. Now let's continue to the third plenary session. And here we're already with Assistant Professor Marco Morandotti, PhD from Politecnico di Torino, Italy. And would like to invite Ms. Dahliatul Hasanah, SSI Math Science, to moderate the session. Okay, Bu Dahlia, over to you.
Thank you, Ms. Rahmati. Good afternoon, ladies and gentlemen. Good early morning for Mr. Marco Morandotti. Okay, first of all, let me introduce myself. My name is Dahliatul Hasanah from Mathematics Department, Universitas Negeri Malang. We have been going through 2 plenary sessions with different topics, of course. Hope everything is fine and happy. I promise you that in this last session, we will have more fun, I hope, and then we will have a good strategy to win a game. So I saw abstract for Mr. Marco, so it is about a strategy to win a game. Okay, it is an honor for me to be the moderator of this plenary session. In this session, you will be hearing, I believe, an interesting presentation from Assistant Professor Marco Morandotti from Politecnico di Torino, Italy. Before we get started, I will read a brief biography of our distinguished speaker today. Let me share screen first. Okay. Okay. So, Mr. Marco Morandotti is now currently is a lecturer in Dipartimento di Matematica. I believe it is a mathematics department in Torino, Italy, Politecnico di Torino, Italy. And then he received his bachelor degree and master degree in mathematics at University of Pavia, and then the second master degree in complex action in CISA International School for Advanced Studies. And at the same university, he received his PhD degree in applied mathematics. And his interest research field in applied analysis. As you can see in the screen, he also is a member of some academic organizations in Europe. And the last one here, this shows some publications of Mr. Marco and majoring in applied mathematics. Okay. Okay. This plenary session is divided into two sections. First section is the presentation from Assistant Professor Marco Morandotti for about 40 minutes. And we'll continue to the second section, Q&A, about 15 or 20 minutes. Okay, and without any delay, now allow me to welcome Assistant Professor Marco Morandotti, who will be speaking to us on spatially inhomogeneous multi-agent dynamics with level switching, mean field limits, and optimal control. All right, Professor, time is yours.
Thank you very much, Daliato, for the introduction. And first of all, let me thank the organizers of this conference for inviting me and giving me the opportunity of presenting my work. I'm really happy and honored to be here. So I think I should share my screen, and I can do this. Okay, can you see the presentation now?
Yes.
All right, so I'll try to put it full screen for better viewing. Okay. So as the title was already read, I leave it here. I won't comment it any further, and I'll promise to guide you through the explanation of every single word about this title, which might sound a little bit complicated. So we're talking about spatially inhomogeneous multi-agent dynamics with label switching, meaning that it's an idea stemming from ideally from game theory. So a situation where you have many agents interacting with one another. They can be individual, usually that are supposed to be rational, and each of them has a strategy, and that's the strategy that they play to to win the game. So because in game theory, people always want to win and maximize their profit. I come from an applied mathematics background. What I do calculus of variations, and I minimize costs, but it's pretty much the same thing, maximizing the profit versus minimizing the cost. And when the agents are very many, it might be interesting either to look at each and every single one of them individually and see how they evolve, but it also can be more practical for some other purposes to have a bird's eye view. So to lift oneself from the single individual and to try and see what happens to the general distribution of the agents. So that's why the notion of mean field limit comes into play. And what's left about the title is optimal control, meaning that not all the games are just set there to evolve according to their own rules. Sometimes there can be some external agent or some control pumping information in the dynamics, and this might be the case, as we will see in the very last slides, when we try to model, say, some situation related to possibly political elections, and then there are different parties and different ideas represented, and people always want to drag you to vote for them, right? So they want to convince you to do what they suggest in their electoral program and to give them your vote. So there can be a situation where there is an external agent, say a controller, a moderator, that drives the dynamics and favors one of the parties in one direction or the other one. So that's why control can be interesting to study in such systems, and we got into this and to include that in the equations. So I think that some of these references appeared already in the slide that accompanied my presentation by just before, and so these are the ones that are pertinent to the talk that I'm giving. So there's going to be a little bit of comments on all of these works that I've been carrying out together with my collaborators, and I would also say that this slide serves to acknowledge them. So Luigi Ambrosi from Scuola Normale Superiore in Pisa, Massimo Fornasier from the Technical University of München, Giuseppe Savare now at Università Commerciale Luigi Bocconi in Milan. Francesco Solombrino is a professor at the University of Naples, as is Stefano Almi just recently, and then Giacomo Albi, that's the last one here, is a professor in the University of Verona. So the idea that we want to do is to model, as I said just before, a system of agents which interact with one another. And they are described both by the fact that they have a position in space, and this position can be just a physical position or an abstract position. So a position could be the political position or the place where they're going to cast their vote. Okay, and the strategy is some tool that they have to play after they made a decision. And the strategy can be interpreted as a strategy, and I would stay with this for the first part of the talk, or it can be interpreted as a label. So a label of an agent qualifies them belonging to a certain category. So if a strategy can be one financial product in your financial portfolio, say that you have liquid money, you have stocks, you have bonds, or you have other financial products, then a label could be interpreted as being a leader or a follower in a population. So the leader is the one that has more appeal, more say attractivity to try and drive the opinion of the position, in this case of the other players, towards that direction, and then the follower just undergoes that decision a little bit more passively. Okay, and there can be different situations in between. So maybe there can be more labels as opposed to the dichotomy of leader and follower. There can be two leaders, as for example, as we will see in the last example. And they want to evolve in a way that they maximize some given payoff, which is a function which for us will almost never be concrete other than in the simulations, but it's an abstract function that describes how much you get if you go somewhere or if you play some sort of strategy. The idea to study these systems come from this dynamical approach to the convergence to game equilibria. So everybody is probably accustomed to hearing the words Nash equilibrium associated with a game, which means a situation where people keep their strategies, because if anybody would change their strategy, then at least one of the players would lose something. So their payoff would be lower than the one that they get maintaining the strategy. So that's the definition of a Nash equilibrium. But coming up with a Nash equilibrium is some sort of rarity. Is like being in an optimality landscape, being at a maximum, right? So you have to hit right away the maximum of your function, and then you never want to move away from that. But if you generate random situation, you hardly are at a maximum point. You hardly are at a Nash equilibrium. So ideally, the game will evolve in a way to drive itself to the equilibrium. And this dynamical approach studies precisely this process. So in the process of optimizing, of maximizing the payoff, but then you go from out of equilibrium towards the equilibrium. And this dynamical moment is what is interesting for us. Okay, and Nash equilibrium is just one, and maybe the most popular that comes to mind when people think about games. But then there can be different notions of equilibria, which can be coded in the system, in the equations, and I'm not talking about them in this context. And as a last thing, I would like to mention that this has some sort of a Darwinian flavor, meaning that Darwin, predicated this notion of the survival of the fittest. In a way, we take inspiration from our first model, from something happening in biology, from some condition, some equation that was introduced in biology, which is the so-called replicator equation, that tells you that the strategy that is providing the highest payoff replicates itself in a way that it is enhanced, whereas the strategy that doesn't provide a good payoff is progressively suppressed. So you wouldn't want to choose a strategy that doesn't pay very well, right? And on the contrary, you want to keep choosing a strategy that provides a good payoff. So the setting here will be that of a spatially distributed players. So they are distributed in some sort of space, and they are driven by this replicator dynamics, which I've just described, and we will see the equations right away. And there's a feedback between the two parts of the description of the system. There's a feedback between the spatial position of the player and the strategy that they're playing, meaning that one can influence the other one according to some given rule. And so people can move as a consequence of finding themselves playing the same strategy but in a better place, and that provides a better payoff. Or maybe they want to change the strategy in a way that sitting at that place, they still maximize the payoff. So now a little bit of mathematics comes into play. So the system, so if we call X the position of the player, and we take it in a physical space, say RD, and we call sigma or later lambda the strategies, the distribution of strategies, that will be a probability distribution over a set of strategies, capital U. Okay, so why do we need a probability distribution? Well, going back to the work of Nash, Nash says if you have a finite number of strategies that you want to play, you call them pure strategies, and you cannot pretend to have, actually you cannot have an equilibrium, a Nash equilibrium of the game if you don't allow these strategies to be mixed in some percentage. So if you only play pure strategies, that's not going to be a winning way, right? So in finance, you would say if you only have a monochromatic portfolio, so if you only have money in your bank, or maybe if you don't have any other products like you do, if you have money but you don't have stocks, or you don't have bonds, or you don't have insurances, then that's a poor choice. So you should diversify, as they say, your portfolio, right? So since you cannot create money, then you have a finite amount of money, and then you subdivide that into the different financial products, and that's a mixed strategy. So that's a convex combination, as we say in mathematics, of these items, right? So that's why if you have a finite number of strategies, a convex combination is a sum with coefficients that add up to 1. And so you need a probability distribution on that. And then you can also be very general. So in most cases, we will consider it a compact metric space. So that's the good notion for a mixed strategy, is a probability distribution. And then doing what I said at the beginning, to lift yourself a little bit higher and flying over the system, you will see the distribution of the population with their strategies. And this is a probability measure sigma on this space here, RD cross the probabilities on U. Okay, so let us start with the definition of the replicator dynamics, so we will see gradually how these things evolve. So the replicator dynamics considers a finite number of strategies and then a payoff function, capital J, which is determined by what strategy I play. I will be player sigma I against some opponent that could be a fish, sigma J, the player indexed by J. All right, so I play strategy UI with a certain frequency, sigma I, and my opponent plays a strategy UJ with a certain frequency, sigma J. So what I do is this one. So I want to measure the success of my strategy. So, And to do this, I do the following. I imagine to play a game where I fix my strategy I and I play against all the possible strategies of my opponent, right? So this one gives a different payoff. And then I subtract all the possible other strategies that I can play. So that's the green term, all right? So what happens now is that this delta is some sort of discriminant between positive and negative. So if my strategy UI, the one here, is doing better than the average of all the other strategies, the one involved in the green term, then I want to keep it because this is doing better than any other thing that I can randomly choose to play. If my strategy is doing poorly, then this term will be negative. And what I do is that I don't want to play the strategy UI anymore, or I want to play it less and less because this is not providing me good money or good income, all right? So the replicator equation that was proposed to model some biological phenomena and has in itself this Darwinian flavor reads precisely like this. So I change the frequency at which I play my strategy. So I prescribe sigma I dot as this number here, that's going to be called the replicator kernel, applied to my strategy to the frequency that I had before. So this is an ODE, right? Sigma dot equals some function and then sigma. And this is an ODE in the space of strategies, in the space of probability distributions over strategies. So what it means to consider a mean-fit limit is that if we have capital N, that are the number of strategies that are played here, that are available, then I want to send N to infinity. So the idea is that if I have an evolution of my strategy indexed by T, this converges to some evolution of strategies as N goes to infinity, and this limit strategy, this limit map should satisfy this equation here. All right, which is basically the reformulation of the equation that I wrote here as an ordinary differential equation in the weak form. So I multiply by a test function phi and I integrate. All right. So the title carried especially inhomogeneous. So for now up to here there was no space involved, right? So now I want to put space. I want to put the spatial dependence because what I'm saying is that my strategy played in Torino, where I am sitting now, can give me a different outcome if I played my strategy in Tokyo, or if I played my strategy in Malang, or if I played my strategy, the very same strategy in New York, because the boundary conditions can be different and players nearby can respond differently to that, right? So inserting space in this is very important. So now the space gets augmented. We're not seeing strategies alone anymore, but we also are seeing spatial components X, and then we call Y the pair of these two objects, all right? And then, as I said before, we take a distribution of these items, which is this capital sigma in the space, in the probability distribution over this Cartesian product. So now we need to find the rule for describing the dynamics. Now, the one for the X component, so the spatial component, we keep it easy for the moment because the first result that we got was already very mathematically sophisticated to fix the evolution of the probability that we didn't want to say influence too much what was happening in the spatial variable, which later I'm going to comment. All right, so we give a kernel, basically a function that does the same, the following thing. So E is a velocity field, basically. It's a local velocity field that depends on the position X where I am. And then what I have to do is to average out, and this is carried out by integration procedure. I have to average out over all the possible strategies that I have. So this is very well explained when the game that I want to play is a game where I want to leave a room. So for instance, when you are in airports and the alarm blares, then you really want to leave the room very quickly because you need to find a safe spot, right? So you cannot stay in the main hall of the airport, you need to find safety exit. So what I do is that I gather information around me and I average it out compared according to the strategies that I have to play. So if I see that the door, or if I know that the door is somewhere right in front of me, but there is an obstacle in between, then when I approach the obstacle, the average of the strategies will tell me not to go straight in front of the obstacle, but will be, say, 50-50 divided between going left and going right. So I can, circumnavigate the obstacle and then go to the door. Otherwise, I would just crash into the wall or into the column, or I don't know, that the journal stand or something like this. So this is what the law that prescribes the spatial evolution does. Okay, so it depends on the position where I am. So where I'm far from the obstacle, I just point towards the obstacle because I know that the door is behind the obstacle. But when I'm near the obstacle, then my strategies will turn from being just point towards it to just go around. All right. And this can be seen as a function that depends on the full state, all right, which, by the way it is defined, is linear on the strategy sigma, because it's the integration with respect to sigma, so it's a linear function. And then what we want to do is to go and augment the information contained in the replicator equation, including space. So now the kernel, the payoff does not depend on just the strategies anymore, but it depends also on the space and assumes this form. So this is the translation of the two summations that I had in the previous slide into the continuum setting. All right, so I sit at position X and play strategy U. My opponent sits at position X prime and plays the strategy U prime, and I average out over all the possible strategies of my opponent, and then I average out over all the possible distributions of my opponent. And then I take away all the possible strategies that I can play. So that's the last integration over U of the W in the sigma W. All right, so exactly the same thing, but now spatial variable is included. And now, if I look at the system, then it reads in the following way. So the evolution of my state, which is given by the evolution of the spatial coordinate and on the strategy that I'm playing, is governed by this velocity field A in the first component, and then this delta sigma, which is the replicator depending on the distribution sigma. And this is just a vector field B that depends on sigma. So if we read the first and the last term of this equality, then we see that this is interpreted as an ODE in a convex set Y. And this convex set is a subset of a Banach space, right? So now there's a pretty solid body of mathematics allowing us to treat ODEs in Banach spaces. And for instance, there are works of Catan, Dieudonné, and others, and also Bresis, that provide an idea of solution and a way and say sufficient conditions for the solution to exist. So essentially, one would like to write an existence and uniqueness theorem like the one that you teach your I don't know, analysis 1 or analysis 2 students when you teach differential equations, right? So you have a Cauchy problem like y prime equals f of xy, and then you assign an initial condition. You want to know that the solution exists, the solution is unique, and then that it depends continuously on the initial data, right? So in a way that if you move your initial state very little, then the two different evolutions will not be too far away from one another. So to do this, the space of probability measures is not quite the right setting. So we need to enlarge it a little bit, and we take the span over all the probability measures, and then we close it with respect to this bounded Lipschitz norm. And then the norm that we put on the full space is going to be a Euclidean norm in the spatial variable and the bounded Lipschitz norm on the measure variable. And this provides good definitions for defining Lipschitz properties with respect to these norms. All right. So now another thing where I want to focus our attention is the following, is the formal derivation of the master equation, which is the PDE that will govern the evolution of the distribution. Because, so this is formal, but will be made rigorous with the mathematics, and it's everything that I swipe under the carpet. It's very technical, and I don't present it here, but it also provides a good way for devising a numerical scheme, right? Because we want to discretize time and then create approximants of the solutions. And this idea is later used for the scheme that we want to, that I will present you towards the end. So now we discretize the time in capital N steps. We take an initial datum, and then we want to construct a discrete solution, which is basically a probability on the space of continuous functions defined over T with values in Y. So this is a probability measure on the paths that can be evolution. So I'm just describing a probability measure which is concentrating on possible evolutions of my system. All right, and then we will see how to make this converge. So the heuristic idea is this one. So at some time interval, IH, so H is the time step and I is the incremental step, all right? I am sitting at position X bar with a distribution strategy sigma bar. So then what do I do? First, I play the replicator game and I update my strategy. So I do a little increment in the direction suggested by the replicator, right? So by enhancing the strategies that give me a higher payoff and suppressing the strategies that fail to do so. And then I land not too far away. So I do a little bit of evolution in a place which is called sigma prime. And then with the sigma prime, I look around myself and then I choose the strategy that I play with probability given by the sigma prime. And then I make a little spatial increment of a step H in there. So that's the update of my state. It's done into two parts. So first, I update the strategy. Then with the new knowledge that I have of the environment, I update my spatial evolution, okay? Which is something very common sense to do, right? So you know that your boundary conditions or your strategies are updated, and then you respond and you act consequently. So you change your space and your position to respond to that. So by the whole set of assumptions that we get that all these things are concentrated in paths that satisfy some sort of equilipsitianity property, which is interesting then to pass to the limit, all right? And then we do this. So we evaluate what we have. So we want to see how the distribution has evolved, right? So we need to see what happens at sigma at time t plus h compared to what was happening at sigma at time t. And the formal way to write it down with when the variables are probability measures is to do this integration in weak form, all right? So we take a test function phi, which must be C1 Frechet differentiable, and then we compute this integral here. So this is just the definition where we substitute phi at, say, time t plus h minus phi with the variables evaluated at time t. Then we approximate this increment with the differential, but then the differential is given by these increments here. So the 1 plus h delta in the sigma variable and the x bar plus he in the spatial variable. So we write it down, and then we can collect the parameter h that comes into play, that pops out. And then we find the velocity field that we've introduced before, which is given by the one whose components are the A and the delta kernel. All right. So now if you look at the green terms, and if you bring the h below the first one, and then we have sigma t plus h minus sigma t divided by h. This is an incremental quotient in the time variable. And this is equal to, if we integrate by parts here, to the divergence of this object here. So then we get, by some abstract theorems in probability, that we get convergence, and the convergence to the equation is this one, which is a continuity equation. Okay, so once we get this, then we want to study precisely this equation. So I see that I'm probably a little bit slow, so let me speed up a little bit. So if you have n players, then we can see everything in a discrete setting here. So integrals become summations. And if we have distributed players, we can associate with the ODE in the abstract Banach space the transition maps, which are the flow maps associated with the evolution equation. And then the solution must satisfy this condition here. So then the existence and uniqueness theorem that we proved is the following one. If we get ourselves in a very general situation, because the hypotheses are very, very mild, we just require the maps to be Lipschitz, then we obtain that for every initial datum, there exists a unique Lagrangian solution. The Lagrangian solutions are those that follow the trajectory, so those that solve the ODE, okay? And we get some regularity results, which I will not discuss here. And then we get, so existence and uniqueness, and then I want continuous dependence on the initial data, right? So since we're talking about probability measure, the right metric to measure distance is the Wasserstein metric. And we get what you obtain by essentially applying Renvall's lemma, all right? So that the evolution of the strategies of the distributions associated with two different initial conditions, sigma bar 1 and sigma bar 2, is bounded by the distance between the initial conditions, time and exponential error. And then this L is a constant that depends on the Lipschitz constant of all of the variables and the functions involved. So why is this interesting? Because, well, assume that you have sigma 1, which is an empirical measure. So you have finitely many agents, right? And then you want to show that these finitely many agents grow in number and they approximate a continuous distribution. Well, then this one tells you that if you go on with another inequality, that you bring the finitely many agents to the limit, then you get the so-called mean field limit that says that the evolution of finitely many agents as the number of them grows approaches the evolution of the continuous variable, which is the limit of the continuous, which is the limit of the initial conditions when they go to the continuum. All right. So in this inequality here, it is contained the result about the mean field limit. So then one knows that Lagrangian solutions are also Eulerian, and then if we have existence and uniqueness of Lagrangian solutions, then we also have existence of Eulerian solution. The uniqueness of Eulerian solutions on the other side is very, very technical and is obtained by applying a very powerful tool, which is called the superposition principle, which is ideally what you know as superposition. So when you do, I don't know, linear things, you always have superposition principle, okay? So if you add up two different variables or two different initial states, then the evolution is the summation of these two. It's the same thing that happens in, like, when you do waves in physics and all that. But it has a formal, say, treatment in the setting of probability measures, which is rather sophisticated. But ideally, what is one doing here is solving a fixed point for the equation. So now we want to move away from this theoretical setting and actually just keep it and augment it to model a new type of agents that are interacting agents that are identified by a label. So now the strategy sigma will become lambda, okay? And these can be used, as I said, to distinguish between informed agents. So keeping the example of the airport that I gave before, it can be done like this. More and more, so airports are employing people to be informed agents. So in emergency events, the general user of the airport that doesn't know the geography or the geometry of the airport very well, so they might be slow in evacuating the space, right? So ideally then, if somebody manifests themselves and say, okay, hey, I work here, I know where the emergency exit is, follow me, then the dynamics is going to be much faster, and then ideally more people get to a safe spot faster. All right, so there might be agents that have more information about the others, and they will be the leaders ideally, that drag the population towards their destination. And it is reasonable to introduce also birth and death rates within a given population and label switching, meaning that this is better seen when you do politics. Political leaders were not always leaders, right? So they were at some point, say, regular citizen, and for some reasons they emerged as leaders. And in some cases, it can also happen that leaders fall in disgrace, so people don't follow their opinion anymore. So ideally, the status of your label is not fixed in time; it can evolve. So you can be a popular leader at some point, and then you can become an unpopular leader later, and people will not follow you anymore. So how is it possible to include this in the evolution? The applications are numerous, are very wide, right? So they can be to chemical reaction networks where the label is the type of reagent that you have, and they change you in a chemical reaction. They can be social dynamics, as I said here. This is something that involves, for instance, political elections or some other things. And also we can also use a Boltzmann type system. So this can have an application when studying gases and, for instance, particles that collide. So now we extend our setting in the following way. We call X the position, lambda the probability, and we couple the non-local transport dynamics that we had before with a Markov type jump process that governs the evolution of the labels now. Okay. And so the velocity field is going to be described by this vector field V, which is now fully dependent on the state and on the all the agents and on all their labels, which was not the case as before. And then the lambdas evolve according to a transition law T, which is still dependent on the whole setting. Okay, so here we have complete dependence on all the positions and the labels and on all the distribution of the system. And examples that was actually the motivating example is the one about the leader and follower dynamics. So here there are two explicit, there's an explicit velocity field for leader and followers. So K is as an interaction kernel, F stands for follower and L is for leader, and lambda J of F is the probability the individual J has to being a follower or to being a leader, okay? And now the transition maps are given in this way. So since we assume that the population is only made of two subpopulations, the leaders and the followers, what is a leader can only sees being a leader and becoming a follower. So you see that the columns of these metrics add up to 1. Okay. So then our aim in this case, in this work, was to find the minimal hypothesis on the velocity field V and on the transition map T to be able to give the same existence and uniqueness result as we had before. And these are technical but not so difficult and are listed here. So the velocity field must be Lipschitz with respect to the status to the state variable. So there's a Lipschitz property with respect to Y, and must be Lipschitz also with respect to the two different distribution of strategies and agents. And then they must be bounded in some sense by their first moment, which is the last property. And then the transition maps T must enjoy the same boundedness property, which is T1, and the same Lipschitz property, which is T2 here. They also need to be to do to have this property. So they vanish on constants, which means that the evolutions, this guarantees that the evolution moves on the tangent plane to the space of probability measures. Because if you deal with a probability measure and you make a little bit increment, then what you need to preserve is that the incremented is still a probability measure. So since you had a probability measure before, then the mass charged by the variation must be 0. Okay. And they also have to satisfy this other technical hypothesis here that tells you that the positivity of the measures is preserved. Otherwise, there's a little bit of inconsistency. And now we can prove the same type of result as before. So there exists a unique Eulerian solution. And if we start from atomic measures, which converge to a continuous one, then their evolutions converge as well. So this is the mean field limit result as well. Again. Okay. So an example of possible admissible transitions is the following one. So assume that we have H labels instead of just 2. Then we have, if we also make the assumption that T is linear in lambda, then this can be represented by the following matrix, which is interesting because it is a matrix that has some properties. And in case it's independent on the state, so if in case this is a constant matrix, this is a very known animal in the set of Markov in the study about Markov chains. It's called the Q matrix, and this is the one that can be integrated via the exponential integration and solve the system. So this is a more general setting than that one that allows full dependence on the state. So admissible velocities can be read like this. So we consider this marginal here, which is the expected values of agents with a certain label under the distributions, under the distribution psi. So we look at a certain region of the space V, and we want to say how many leaders there are there, or followers. And then we describe the velocity field as the convolution with this sort of kernel that has the interpretation of giving an average velocity of the system, which is weighted by the probability of a particle having a certain label. Okay. And then one relevant example was taken in this work by my other collaborators, where they came up with a situation as before here, with fewer dependencies. So the kernels were symmetric, and then they obtained this evolution equation. So the first two items are the continuity equation that I introduced before, and then the other two are a forcing term. So basically the evolution is also driven by the probability that you have of getting out of the label H and the probability that all the other players have to be coming with label H. So switching the labels from the one that they have into the one that we're looking at. So now, in the last few minutes that I have to present my result, that I want to talk about the approximation scheme. And I'll be quick on this because it is very, very technical, but the idea is the one that I gave before at the beginning. So first we perform a strategy optimization, but with this general map here, and then we perform a position update. So this must be carefully translated into the interplay between what happens at the level of positions and strategies, together with what happens at the level of the distribution capital psi, which is written here in this technical slide. So there's a partial update in the world above after we have updated the position, the strategies. So it remains the identity in space because we don't move yet, but then we have updated the distribution of strategies, and then we update with the new knowledge of the surrounding panorama the position, and we can finally fully update the measure, the distribution at the at the higher level. And then the theorem that we can prove is what one expects ideally. So the scheme converges, all right? So the scheme converges, meaning that if you have an approximation of a continuous distribution, then this approximation, as the time step vanishes, converges to the solution to the continuity equation that we have. And then the final thing was about adding control. So as I said, that there might be an external agent that tries to interfere with the system or to drive it towards the preferred states. And this is done by adding control only in the special variables. So the special variable is the position one, right? And as I said, in the models of political opinions, this is the one measuring in which side from left to right, say, you're going to vote. So there must be an agent that wants to push you to vote more to the left or more to the right, or make you follow some certain leaders that have some political ideas, right? So there might be somebody funding the political campaign of a political party, resulting in more advertisement, more publicity, more visibility of their candidates. So maybe you just know them more than the others and you want to vote for them. So this is paired together with an optimality of the expended cost, meaning that you want to do this, but with a limited amount of resources. So you need to place the control strategically in order to minimize the cost that you want to pay. Not everybody of us is Elon Musk with a whole lot of money. So maybe governments can fund political parties only this much, and you need to strategically allocate this to maximize your payoff. So this is really the combination between maximizing the payoff under the minimization of the costs. And the cost depends on a Lagrangian L here that depends on the position, on the state of the system and on the distribution, and then a final cost, and then a cost that that measures how much you spend to interact with the agents. Okay. So the theorem that we prove is the following one, that this functional here has a gamma limit. And this can be recovered eventually by the discrete setting. So if we do the same thing as before, if you have a mean fit limit, then we can also find that the associated limit of the functional is the gamma limit of the functional, which is associated to the limit of the distribution. This again is very, very technical, but now I believe that I can amuse you a little bit with some graphs and simulations that we did. So in the first simulation, we tested some random initial conditions here, where we have one population of followers that are always depicted in blue, and one population of leaders. And leaders want to bring the political opinions, say, or the position to this dashed red line, which is -0.5. All right. So these are the initial states, and then we let the system evolve, simulating the continuity equation without control first. So these are snapshots in time. So there's time t equals 0.5, 2, 3.5, and 10. And then we see that the leaders get more and more peaked towards the target that they want to achieve. And when that happens, some followers get generated in their position. So this means that the leaders have succeeded in attracting followers. And then the followers that were far away, some of them still stay far away. And by the way the dynamics is prepared, necessarily when there are too many followers, some of them will become leaders. So there are emerging leaders. So where you can see maybe here, there's a little bit of orange under the blue curve, okay? And this is the evolution of the labels. So this is the evolution of the positions, and this is the evolution of the labels. Now, let's add some control. And then we see that something different happens. The graphs are different, right? So if we add control, what happens is that the leaders get peaked not as close as their target as before, because the control here was to try and maximize the interaction. So to try and get the followers the closest to you as possible. So ideally what happens is that the leaders gave up a little bit their target in order to get a better superposition of the supports with the followers, if that was something that wanted to be maximized, as in this case. Okay. And then this is the comparison of what happens. That's the time evolution here. So in horizontal, we have the special variable x for the uncontrolled case and for the controlled case. And you see that the evolution is a little bit different. Okay, so it's not maybe very visible, but the two curves are very different from one another. So here they try to stay peaked, whereas here they try to merge each other a little bit more, because the idea was that the leaders drive the followers towards themselves. And here we do a second test where we have the population of followers always in blue, the population of leaders always in, so one population of leaders in orange, that's this one, and they are sort of radical leaders. Okay, so what they want is to keep their position and to keep predicating their position, whereas the green ones are other leaders, so say a second political party, but this will be more populistic. So what we mean by this is that they are willing to give up their principles, as all the populist governments try to do, in order to get more and more voters for them. So someday these political leaders say something, someday they say something which is not quite, coherent with what they said before, if this pleases the masses. And so they're willing to change their opinion to please the masses. And then what happens here is that in the uncontrolled case, the evolution will be as we will see, which is this one. So there will be the more radical leaders that stay close to their opinion, they don't move, whereas the populistic leaders try to move away from their original position in order to get more voters for them. So to have the support of these two measures, so where they lift from zero, superimposed more and more with that of the followers. And if you see here, they attracted a big quantity of followers under this column, all right? Whereas if we insert control, what happens is that we try to see if the external controller supports and enhances the strategy of the radical leaders, not influencing the one of the populistic one. So the radical leaders will not stay as peaked as before as they were, but then people follow them more and more. And if you see here, maybe you will see a little dotted line, which is the green line, which means that populistic leader will form where they have followers, even though they abandon their original political idea and to move very much away from it, just to be where the followers are. Okay, so these are the evolutions in this case with the two populations. So here the green and the red are the green and the orange are superimposed, but here there's a little bit of emergence of these ones. So with this, let me sum up what I said so far. So we provided Lagrangian and Eulerian description of the evolutions of these type of systems, together with convergence and mean field limit evolutions, when the number of particles diverges to infinity. Ideally, you want to find a number of particles to be able to do the simulations, and then you want to send them to infinity. Some analytical tools were needed, and we developed those. And I didn't mention them, but I didn't show them, but I mentioned them, like this superposition principle and continuity equations in Banach spaces. And then we have extended these results as to include also the formation of leaders and followers as a result of label switching, we devised a solid and sound Lagrangian scheme for the numerical approximation, which reflects the two steps in which the label and or the strategy and then the positions are updated, and then we included mean field optimal control in the spirit of a series of work that precisely treat this case from a more variational point of view. So, and with this, I would like to thank you very much for the attention and apologize if I went a little bit over time over the 40 minutes that I had. Thank you very much.
Okay, thank you very much for Mr. Marco Morandotti, for delivering such interesting presentation. Okay, ladies and gentlemen, we now come to the Q&A session. You can press raise hand button if you want to ask directly to Mr. Marco, or you can type the question in the chat room and I will read them for you. Okay, please. If there are any question. Oh, okay. Pak Hafiz, perhaps raising a hand. Please,
Yes.
Pak Hafiz. Yes.
Okay, thank you for the chance. Okay, very nice presentation, Marco. Thank you. And my question is, the number of followers, is it is preserve the number of followers or not? Because I see your simulation that if there are two leaders and the followers try to spirit and try to follow both of the leader, but the initial followers is, I think, still high. Would you like to explain?
So yeah, so the situation is the following. As you see here, this is the percentage of followers that are in the system. Okay, so they start at 0.8, say 0.75 or 0.7 of the population, as you see in this slide, and then they augment a little bit. So the idea is that there might be, so the power of this system is that the number of followers, the initial number of followers can change, as can change the initial number of leaders of both species. So the point is, when there are too many followers in one situation, then there is an emergence of leaders. So some of them will have, say, their opinion a little bit more popular at some point, and then the people around them will start listening to this person more and more. So this was a follower, and then will be promoted to a leader at some point. And leaders form where there are many followers because they want to, because they will be able to drag the mass towards their opinion. Okay, so the numbers are not fixed. So they are given at time zero, but then they evolve together with the system and together with the different weights and the interaction kernels that one can have, for instance, here. So whatever these kernels K or alpha do, they measure the probability of switching from one label to the other one. So the probability that a person has of becoming a leader, of ceasing to be a leader, or becoming a follower and vice versa, is governed by these quantities here. So precisely the kernels, the interaction kernels K, KH, this was a symmetric one, or KHK, which tells you how the individuals of population with label H interact with populations, individuals of the population with label K, right? And then this convolution with the measure mu precisely governs this fact. So according to whether H means leader or follower in that example, then this means that you might want to move in a different position following the opinion of the leader, for instance, right? So ideally leaders are called like that because people follow their opinion, and then if somebody at some point gets promoted to being a leader, so his opinion is so influent that people start following him, then we have a label switch, right? So, and the label switch is governed by this transition matrix Q in the easy case that T is a linear function of lambda. So there would be T of lambda is Q applied to lambda in this case. But yeah, so to answer briefly to your question, there's no fixed number. So the number of leaders and followers is not preserved. They can evolve dynamically according to what is more convenient for the system and according to how the weights have been regulated.
Okay, thank you. And the second question, is it okay?
Yes, of course.
And maybe next slide, would you like to? Yes, this one. If I see there occurs for the leaders, at the beginning, there is only one, and then there is a second leader. And is it probably because of the like you said, force in your equation?
So the interpretation of these graphs, so the first one is for the position, the second one is the label, all right? So the idea is that the graph in the first line measure the political opinion that leaders are promoting. So since they want you to vote for somebody that's sitting at position minus 0.5, there's a concentration of leaders around this position because there's only one party and they tell you vote for me, vote for me, vote for me, ideally, okay? In the example of political elections. So what happens is that they stick to staying here, and the dynamics is done in such a way that where there are leaders, followers follow. So briefly, as soon as time starts, there will be some formation of followers. Here, there's a little tiny bump, right? And then the bump grows a little bit more here. But as I said before, if there are many followers in some position and they, for this initial condition that we threw at random, are far away from the target of the leaders, then some leaders will form, right? So some leaders will also happen to be around this position because it's something that the people like in a way, all right? Whereas this is the percentage of leaders and followers. So this is the lambda variable. So this measures the probability of being a leader, which is the orange one, so it's the one that is below. So if lambda is 0, you're a leader. If lambda is 1, you're a follower, basically. And here is the probability of each individual of being a leader or a follower. So you're not black and white neatly, but there's a continuum, there's a grayscale between these two, okay? And then after some point, there's a switch and the threshold that you can decide that tells you that if your probability of being a leader is large enough, then you will be a leader because people will follow you. So in the continuum approach, this is like this. It's not 0 or 1. Otherwise, we would have to have, say, a delta in 0 and a delta in 1. People are only just leaders or just followers. Ideally, you can be mixed. But then you see that the supports of these two measures are almost disjoint, all right? Because where there are leaders, there are almost no followers, and there's a tiny intersection, which is a numerical artifact because I didn't show you the simulation up to time, I don't know, 100, that would have presented the more neat separation. And this is the same thing as happens in the other cases, all right? Also in this case here. So there are leaders here that are the radical ones, and followers get accumulated next to their position. There are followers that at the beginning are undecided between voting one side or the other side. And then what happens here is that the populistic leader abandons their initial, say, political program to meet the requests of the population, right? So they move themselves to go closer to the population, whereas the radical ones that stay where they were.
Okay, thank you, Marco.
Thank you.
Okay, thank you, Pak Hafiz and Mr. Marco. Is there any question? Perhaps while waiting, I want to ask a simple question. I think you have described about finite agents before, and
yes.
the question is how to identify from those agents that one of them is a leader or let's say more informative agent. Is there any way to recognize that level?
So yeah, so if you look at them, definitely you don't know, right? So their capability of being a leader or a follower, or their capability of or the fact that they're informed agents manifests in some situations. So that's coded in the system, in the equations and in the weights that they have. So what one would see by going into an airport is all the people there, and they're all X's basically. What they do not see is the sigma that they have, or the label lambda that they have. So, but everybody has its own, right? So in the case of the airport, it's a situation when you want to, leave the room because there's an emergency, that leaders at some point manifest themselves and they say, I know where the exits are, so please follow me. Okay, so in that case, so they were sort of dormant in a way, right? So they were not manifest, they were just sitting there doing random things, being idle. But then if needs be, then they say, okay, I am the one to follow to drive you to safety. Whereas political leaders are always manifest.
Yeah.
Political leaders are always visible, right? And what happens is that maybe at some point, some of them are not listened to anymore because, I don't know, say that there's a scandal and that they are constricted, they are obliged to resign or something like that. Then they fall in the gray where nobody sees them anymore. This is the switch from being a leader into being a non-leader, in that case a follower. So you would have to follow someone else. Or maybe there is someone, I don't know, a young person that says, I'm bringing novelty into the political system, I'm cool and I have new ideas, these are, the challenges for the future, vote for me. This is the emergence of a leader in a way. Could be, or maybe it's an optimistic one, I don't know.
Okay. Yeah, thank you, Mr. Marco. Okay, due to limited time, I guess we have finally come to the end of the last plenary session. Once again, I would like to say thank you very much to Mr. Marco Morandotti for delivering such a wonderful topic, I think, and
thank you for having me.
Yeah, thank you. And this is very close to our daily life. Yeah. Okay, I will pass to Miss Rahmati. Thank you, Miss.
Thank you very much, Ibu Dahlia, and thank you so much, Assistant Professor Marco Morandotti, PhD. Well, we've listened to something very conceptual in the previous two presentations, and from Mr. Marco, I think we've listened to something more practical, and it's like the implications of math in life, especially in social dynamic. I think most of the explanations were about that. Thank you so much. Let's give one big hand for all the keynote speakers today, everyone. So we have listened to all the 3 speeches in the first day of this conference. Once again, thank you so much. And we'd love to express our heartfelt gratitude for the presenters, for Mr. Marcianus F. Fezerman from Nanyang Technological University, for Professor Dr. Toto Nusantara from Universitas Negeri Malang, and also for Assistant Professor Marco Morandotti from Politecnico di Torino, Italy. Thank you so much for the very compact discussion, presentation, knowledge, and insight. Well, ladies and gentlemen, allow me to inform you the general information of this conference for tomorrow. So here's the link for the schedule for tomorrow's agenda. I think the operator is going to share it in the screen. Yeah, right there. I think you also have it in the rundown schedule. I believe that most of you have got the rundown and the schedule, and you can find the link of the Zoom session tomorrow. And then the second is that all presenters should rename your Zoom ID according to the breakout room. And then the third, participants must attend the 2 plenary sessions for tomorrow, and a parallel session as a requirement to get the certificate. So tomorrow we're still going to have plenary sessions as well as the parallel session. And then the fourth, participants must also fill in the attendance link via the link provided in the chat room. So the operator have shared it in the chat room. Please try to find it if you haven't filled in the link. And then next, for the fifth, for this conference, we will also award the best presenter for each parallel room. So for tomorrow's session, in the tomorrow's parallel session, we will award the best presenter. Number 6, the last, we would also like to give you a friendly reminder about the submission of the full paper, which is November 13th, 2021. So that's the deadline, November 13th, 2021. Hey everyone, this is all from us. Well, one last pantun for me. 5 + 2 = 7. Everybody see you in the tomorrow's session. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
See you tomorrow, everyone.
Thank you, Marco. Hope to see you here coming to Indonesia.
It would have been very nice, actually. Yeah, but for the moment, we have to do like this.
Yes. Okay. See you, Marco. Thank you very much.
See you
for joining
tomorrow.
this
Bye-bye.
conference. Bye-bye.
Bye.
Nice to meet
See
you.
you. Thank you so much.